and you enjoy the day today. Thank you.
Hello? Do I use this one or?
Hola.
Ah, okay. Okay, good morning. Thanks, Cristian, for the kind introduction. It's I'm super honored to be here today. So as Cristian said, I studied here at UPC and then left quite some years ago. And so for me, it's very special that I can talk to all of you, see some familiar faces, but especially many non-familiar faces. So that's great to see the young talent that we have here in Barcelona. And so today I would talk about multi-object tracking, which is a topic I have been working on for over a decade now. And as Cristian said, I recently moved to NVIDIA, but that was just like a couple of months ago, so I can still not tell you too much about what we have been doing there. And so this is mostly work that I did with my PhD students at TUM. So let's get started. So this talk is going to follow a little bit the trend of the whole computer vision community, right? That it's been going towards end-to-end learning, trying to train models that do tasks and train them fully end-to-end from image to whatever output you want. And this has been no different for multi-object tracking. So let me start by roughly defining the problem. So in tracking, we want to detect and track all the objects in a scene. These are the kind of scenes that I will be working with, mostly people tracking, because people have very interesting motions and they are very difficult to track. But also because it's really important for many applications to be able to correctly track people. And I think tracking is sort of at the core of dynamic scene understanding, so trying to understand the behavior of all the dynamic objects in the scene, of the key players in the scene. And of course, this is super important for applications like autonomous driving, for AR, VR. You really need to understand what is happening around you. And one of the most difficult things to understand are the moving objects. And so, for example, you have this example here of the car and several key actors around the car that could potentially cross the car. And so not only you need to understand in a single image that these are people and that there's a car and that there's a stroller, et cetera, but you also need to understand their trajectories. You need to understand how they have been moving in order to predict the future trajectory of all of these actors. And today we'll talk mostly about tracking bounding boxes, but we use pretty much the same techniques to obtain segmentation masks that are consistent in time, to obtain key points for pose estimation. This is pretty much the same technique. So today I want to focus more on the dynamic aspect, on how to deal with the temporal domain. And so I will be presenting several paradigms that we have been using in multi-object tracking, starting by the super well-known tracking by detection. This has been around for almost 20 years. Then moving on to what was presented maybe like 3-4 years ago, tracking by regression. And now what is, or what I hope is, the paradigm that people are using, which is tracking by attention. And so all of these paradigms have been moving forward, as I said, like the community, towards, first of all, unifying the problems of detection and tracking, which were treated separately in the tracking by detection paradigm, but also towards end-to-end learning. And this is really important because there has been an evolution of techniques, but there has also been an evolution of data sets. And this is something that I will roughly talk about. At the end, though, I have a bit of a surprise for you, that tracking by attention has its problems. And so if we want to solve them, we will actually come back to where we started, which means we will come back to tracking by detection. And I will actually show you how, with everything that we have learned along the way, can we make tracking by detection state of the art again. Now, in terms of data sets, it's quite incredible what the community has been able to do in just 5 years. So when we opened Mod Challenge, that was back at the end of 2014, we were dealing with this type of sequences, you know, like 4 or 5 people walking around. This was already a super hard scenario for us. And with the years, we have been proposing harder and harder data sets with more accurate annotations, with interactions between static objects and moving objects, all the way to 2020 with our newest challenge, which is completely crazy. I mean, these are the type of scenes that we can now deal with. So you can see just in this slide the crazy evolution that the tracking community has done, going from dealing with this type of sparse scenarios to these completely crazy, crowded scenarios. Okay, so let's get started with the actual paradigms. How do we solve the tracking problem? Now, the easiest way is to do tracking by detection. So if you imagine tracking as finding the bounding boxes in the full video, this is an incredibly complex task because you have to look at all the pixels in all the frames of the video. So we usually simplify it by applying a detector first. And detectors are really good at what they're doing. So we can use them as a starting point so that they give us a set of proposed locations that we're going to look at. And from this point onwards, we throw away the rest of the pixels, and we're just going to look at these locations. Now, in a second step, we do the actual tracking, what we call data association, in which we take the different detected people or objects, and we try to associate them in time. And you can see here already some of the problems that the data association step has to solve, meaning when you have a false positive or a false negative, this is when data association has to be a little bit smarter. Okay, so let me present a super simple tracker. And not because it's simple, it's something that is actually not used. So I've seen that in the autonomous driving industry, pretty much all the trackers have this kind of structure. And so we start, of course, with a detector. In the first frame, we apply our detector. And the second step is about predicting where this object might have gone in the next frame. Now, the easiest prediction is to say that the object has not moved. More complex predictions can come from Kalman filter and things that I will talk about later. But then the actual data association, the actual tracking happens in the third step, when you actually perform this matching between your predictions and the new detections that are coming in the new frame. And this matching is where all the magic happens, right? I mean, we have to be careful when there's occlusions, when there's people on top of each other. For example, in the mod 20 sequence, where there's all these crowded scenarios, you can imagine that matching is pretty tough. Now, I don't want to talk about the second step too much, but I will just say that classically people have been using the Kalman filter. Now they use recurrent architectures, learned architectures, but for now we can assume that we're going to use a constant velocity model. And we're going to assume that because, as we will see then at the end of the presentation, this is actually what works better. Now, let's go to the third step, the matching step. So I said that this is where all the magic happens. And essentially, this is a bipartite matching problem. So what you have are predictions on one hand, detections on the other hand. And what we have to do is we have to populate this matrix that tells you how likely it is that one prediction is matched to one detection. And you can put anything that you want in there. You can put distance between bounding boxes, you can put intersection over union, 3D distance, appearance features, whatever you want in there that tells you how likely it is to match one pedestrian with the other. Now, once all the numbers are in, then what you do is you solve the matching problem, for example, with the Hungarian algorithm. And this gives you a unique solution that assigns those predictions with those detections. So as soon as this assignment is done, you have tracked these pedestrians from one frame to the next. Now, this is, of course, a basic tracker, but most of the trackers that we analyzed from 2015 to 2020 followed some kind of a similar structure. So this is a plot of the trends, the kind of methods that people have been using since we opened the Mod Challenge benchmark all the way to 2020. And we see that at the beginning, people were very focused on learning better motion models. You know, I said that people were using the Kalman filter. Well, these were the years where people used more interesting models, physics-based models, learning-based models. This all happened in 2015, 2016. Then people moved towards learning better appearance models, right? So there are two things that you can use to match a prediction and a detection. One is the motion, the other one is the appearance. And finally, people focus on the third step, actually improving the matching step. For example, using multiple frames. And so they created more and more complex optimization problems in order to make this matching more robust. So the question is, though, how much learning was in all these methods? Well, the answer is actually not much. So people were doing these things in a very handcrafted way up until 2018, more or less. So of course, deep learning was very present in the first step, in the sense of I give you better and better detections because I train a better deep learning model. But the other two steps were still pretty handcrafted. And so people started working on the prediction step, the second step, with better deep learning models. And this kind of spawned a topic on its own in the computer vision community, the topic of trajectory prediction. And so this was about learning the motion model. Of course, it was in 3D. It was not directly applicable to 2D images, but there was a lot of progress happening in that area. For the third step, as I said, people focused on improving the appearance models. And this was also thanks quite a lot to deep learning. So people started to learn better appearance models. And as I said, the last one was improving the matching, multi-frame. And here, there was still not a lot of learning happening, right? So there were mostly, people were mostly proposing complex optimization problems. There were some appearance models, some motion models in there, but still the optimization problem itself was solved with classic optimization techniques. Now, what I will present in this talk is a bit what has been happening since there. So how has the community used learning for multi-object tracking? And I will present three works. One is on tracking by regression, in which we're actually using the prediction of the next position to do the matching also. So these two steps are kind of coupled by doing this tracking by regression. And actually, everything from tracking by regression comes from a detector, which means that in the end, all three steps are somehow coupled. The other work that I will present is how to solve the matching problem with graph neural networks. So instead of using classical optimization, you're actually using a learned solver. And this, of course, includes or puts together implicitly steps 2 and 3 in just one step. And the nice thing is that you can also backpropagate all the way to the detector. So this also kind of couples the three steps. And finally, maybe not surprisingly, we're going to use attention to perform all three steps in what I think is a very nice and elegant solution that solves the mode problem from image to trajectories. Okay, so I want to focus mostly on the tracking by regression and the tracking by attention. So I will just present briefly what I mean by using graph neural networks to solve the matching. So in graph-based association, instead of using the bipartite matching, as I've presented before in the simple tracker, and trying to match the detections in 2 frames, we're trying to find full trajectories across the whole video, which means that we're creating this huge graph where the nodes are our detections, and we're trying to find trajectories within this huge graph. And so the thing that is most important is what do we actually put in these edge costs? So you can imagine that these edge costs are the same thing that the costs that we used before for the Hungarian. So you can put in there the IOU, appearance model, whatever you want. And the idea is that once we put all the information in these edges, we now use a classic solver. For example, the simplex or more complex solvers if you want to increase the connectivity, for example, in the graph. And this solver gives you directly the trajectories in the whole video. Now, you can start infusing a little bit of learning in here, and the easiest way is to actually put a little bit of learning into these edge costs, right? So why do I have to decide if I put the motion model or the appearance model? I just put everything in there and let an MLP decide what is best as an edge cost. Or you can actually go one step further and put all the information in the nodes with a tiny CNN. You can put the information in the edges with an MLP, but you can also solve the whole thing with a graph neural network. And here we did a couple of works, one which was using one graph for the whole video, and now we have presented a solution that is hierarchical, that is extendable to really long videos, and that in the end works much better. So this is all I want to say about graph-based association, because I want to spend quite a lot of time talking about tracking by regression and tracking by attention, which are the most learning-based solutions. So this was a work that we did back in 2019, and I talked about this work in many talks, so I will not bore you again with an explanation, but I do want to give you a bit of an idea of what tracking by regression is. So this came from looking back at the regression-based detectors, right? Because at the time we were using detectors like fast and faster CNN, which are in the end regression-based detectors. And by regression-based detectors, I mean that you have your input image, you pass it through a series of convolutions to obtain your feature representation of the image, and from there you can, again, not analyze the whole image, but just focus on the interesting regions, what those detectors call region proposals. Obtain the representation of these region proposals in your feature representation, and from there, do all the magic. Essentially, you can classify the bounding box. Is it a car? Is it a person? And you can also regress that bounding box. And this regression head is funny. So this regression head was created essentially to improve the accuracy of detectors, because it could be that the bounding box is not perfectly placed on the object. And this means that your accuracy will automatically be lower. So kind of a hack to fix this is to have a regression head that moves the coordinates of the bounding box. So let's look at how this regression head is doing this. So let's imagine that my region proposal is not really well located. It's roughly on top of the object, but it's not really well placed tightly around the object. This is going to give me a better accuracy. So what I do is I actually create a regression head that learns to move the box towards a better position. Once I know the box is there, once I have classified it, it's much easier to regress it and say, hey, this is exactly where the box should be. And so once we saw this behavior, right, like moving the box from here to here, we were like, hey, you know, this is exactly what we need in tracking, right? Especially in online tracking, which means when I'm tracking frame by frame, the objects are not really moving a lot from frame to frame. And the motion is very, very similar to the example that I've shown. So why not actually train a detector and use it for tracking? And this is how we became with this hybrid name tractor, which is a detector with tracking capabilities. And how we actually use it is, let's assume that we've been tracking these 3 pedestrians for a while. And so we have these 3 bounding boxes. They are color-coded because they already have an identity in there, right? I have already been tracking these objects. And now I'm at frame t+1. So what I do is I look at, I use the detections of frame t as my proposals. So I forget about any region proposal network that FastRCNN has. And I use the detections of the previous frame as my proposals. And now I ask my regressor to just do its job, right? Regress the bounding boxes to a better position so that they tightly fit the object that it was tracking. Now, you might say, look, Laura, I mean, this is not really tracking, right? You have not associated anything here. What about all the data association that you were talking about before? And I say, well, if I can answer one question, which is, where did the detection, for example, with the red ID, where did it go in the next frame? Can I positively answer this question? If it's yes, then I'm doing tracking. If it's no, then I'm doing something else. But it turns out that the bounding box on the right side was created using the red bounding box on the left side as proposal. So I can inherently say that these 2 boxes are now associated. So actually, I am doing tracking because I can positively say that the 2 red bounding boxes belong to the same person. Now, of course, this is a super simple tracker. It's good because of its simplicity. We don't even need to train anything. We just get a well-trained detector, and I can actually do tracking. If you do have to retrain your tracker, for example, for cell tracking, you don't need to annotate full videos. You can just annotate single images. And of course, it's online, which means that you can use it for real-time applications. It has many, many disadvantages. We can talk about this offline. But the nice thing is that this has spawned a series of works that have been building upon tracking by regression methods. And I'm not only talking about tractors, so there's also, for example, works like center track that follow the same idea, but instead of predicting bounding boxes, they regress center points of the object. But the idea is pretty much the same. And the idea here is to give a lot of importance to the spatial features and forget a little bit about the appearance features. Now, the cool thing about this is that if we look back at the scheme that we had before, this spawned like many, many works, which you see here in the bright stars, which actually improve state-of-the-art by a lot. So these very simple trackers are very robust. And of course, I've said that these feature mostly spatial cues. And what all of these subsequent works did is basically add in the appearance features back into the mix. So this was one nice step into fusion detection and tracking, right? I'm using a detector in order to do tracking. But I'm losing this notion of the appearance. So one thing that people did is, okay, how about I bring back the appearance, I bring back this idea that I need to do data association, and I bring it back by adding an embedding head that I'm going to predict aside from my classification head and my regression head. How about I predict an embedding? And this embedding is going to represent the appearance of this bounding box. And so I have now association happening with a heuristic by just computing embedding distance, right? So every bounding box has its own embedding distance. I can just do L2 of these distances, and suddenly I have an association. The cool thing is that it's nearly real time, right? Because I share the backbone with detection, with tracking. Everything happens with one backbone. So this is incredibly efficient. And I'm jointly training for detection and tracking, but still the tasks happen in separate heads. And after further analysis, you indeed see that the backbone is treating this as two different tasks. So we would like to, further unify detection and tracking. Right, we have the first option, which is with this embedding prediction, and there are many famous trackers that have appeared from there, like JDE or Fairmont, which were state-of-the-art at the time. But there's actually a second option to bring detection and tracking even closer together. And this option is, you might have guessed, using attention, using transformers, right? I mean, who hasn't used transformers nowadays? And so the idea is actually to do tracking by attention. And with this, I mean that attention is going to jointly solve the problem of detection and the problem of tracking. And this is going to happen all at once. So we're not going to have the classic steps of tracking by detection. I do first detection and then do data association. Nothing. This all happens with one backbone, with one prediction step, and trained end-to-end from trajectories to the image. And so this pretty much starts with the work of Detter, which is object detection with transformers. So I'm sure you're all pretty familiar with it, but I just want to briefly explain how it works, because this is the basic of tracking by attention. And so the idea there is that you prediction problem as a set prediction problem. And by this I mean that our network is going to predict a series of bounding boxes directly without saying, how many bounding boxes are there before. It's a set prediction problem, right? And so what we're going to have is a transformer encoder that is going to encode the features of our image. And then we're going to have a decoder, which is where all the detection magic is happening. So here what we're having is these object queries, which are essentially random vectors. And they're going to be transformed by the decoder into bounding boxes, into whatever you want, actually. So we have a classification head in there. We have a regression head that actually gives us the bounding box where the object is location, and you can have any other information coming out of that decoder. And so this is really cool, right? Because before we had non-maximum suppression, anyone that has worked with detection or tracking back in the days probably knows the pain it is to actually have a well-set non-maximum suppression. So there's an art of its own in the non-maximum suppression. And here we don't have to do anything like that, right? So the transformer decoder is going to handle everything for us and just give us the number of bounding boxes that we want. And so once we saw this, we said, well, it's really cool and can be super easily extended into tracking. And so now what we can do is pose the multi-object tracking problem as a frame-to-frame set prediction problem. So let's see how that works. So we start with the first frame with the object queries, same thing as data is doing, and you just predict your bounding boxes. In this case, we have 3 objects in the scene, the red, the green, and the blue. Once that is done, we go to the second frame. If we were to do the same thing on the second frame, we would have data, we would just predict independent detections. So we have to do something to kind of connect the 2 frames. And this is where this connection in the middle is helpful, where we have what we call the autoregressive track queries. And these track queries, you see them color-coded next to the object queries, is because they already carry an identity in there. And what I want these track queries to predict is a bounding box that contains the same pedestrian that they have detected in the first frame. So it's really important to train this so that the red query predicts the exact bounding box of the red pedestrian and not any other bounding box. Now you can imagine now that if you think back with the mentality of tracking by detection, of having a motion model or having an appearance model, you can think that all of that information has to be put into the track query. The track query contains the appearance information, contains the motion information, everything is in there. And we just have to train it so that it predicts the right bounding box. Now, for example, in this case, we have 3 objects that are still in the scene in the second frame. So we predict correctly the objects and we assign them an identity. But of course, we can also predict entering objects by predicting a box from the object queries, right? So we will have the track queries and the object queries playing together nicely. And the same thing happens when an object disappears. For example, in this case, the blue object has disappeared from the scene, and the only thing that happens is that the blue query stops predicting any box. So very elegant formulation. It can handle all the scenes, all the possible cases that we have in tracking, and we just have to train it right, which is not that easy, I tell you already. But if you have enough data and you pay enough attention to the corner cases, this is actually a very nice, very simple and elegant formulation. So let's see a little bit what kind of attention we have and why do we need this type of attention for tracking, right? So it's not just a transformer applied to tracking, but we actually need to understand what each type of attention is doing and how can we use it for our problem. So the encoder has no magic, right? Same as data, it encodes the image features with some self-attention layers. The decoder now receives the object queries as well as the track queries. And we have tried many ways to combine this. The easiest way and what works best is just to concatenate these 2 types of queries. Now we pass these queries through a series of self-encoder, decoder attention. And finally, we have the MLPs that predict the box, the classification, whatever information we want. The question, though, is what kind of attention do I have and how am I going to use it? So let's look at the 2 types of attention that we have in the decoder. We have, first of all, the self-attention, which is going to play with the queries, which is going to act on the queries. And then the encoder-decoder attention, which basically passes all the image information to the decoder. Now, why do we need self-attention? Well, first of all, to initialize and terminate tracks, right? So when a track is occluded, you need to terminate it. When we have a new object, you need to create that object. But it's really important that the two types of queries talk to each other. Because if I want to predict a new bounding box, let's say the purple box that has appeared here, I need to know that no track query is associated with that box. Right, so the track queries need to have some sort of priority there to say, if I find the pedestrian that I was tracking, I need to grab and predict that pedestrian. Otherwise, we will have an identity switch, which is an error in tracking. So the track queries and the object queries need to talk to each other. And that's what self-attention is for. What about encoder-decoder attention? Well, obviously, if we want to find a new object in the frame, you need to have the right image features for it. But also, and most importantly, to adjust to the changed position of the tracks. So if you have played around with Detter, and there was also quite a bit of an analysis there in the paper, the object queries have some sort of a spatial position that they favor, right? So there's an object query that only fires bounding boxes in the bottom left part of the image. And it's the same for track queries, which means that they do have a spatial preference for the position where they have been firing so far, which is great. It's good for tracking, right? The bounding boxes are not moving around crazy. But this also means that when the object is moving, you need to adapt, you need to update the track query, right? It's this motion model idea that I was telling you before. This needs to be embedded in the track query. And so for this, you need the image features. You need to tell the track query to keep updating its position. Now, let's look at a question that any tracker has to answer, which is, how can you recover from occlusions, right? Like, all that I've told you until now is frame-by-frame tracking. But what happens if an object is occluded for a long period of time? Now, the cool thing is that I don't need any re-identification head, which is what people usually use to track objects that are far away or that reappear far away after an occlusion. I can just keep the track queries alive for a certain time window. So for example, in this case, oh, sorry, I don't have it here, but in the case where the blue pedestrian disappeared from the scene, it could be that it's occluded and it will reappear at a later frame. Well, I just keep the blue track query alive, and I ask it at every frame to, predict a bounding box. If you can find that pedestrian, just keep predicting that bounding box. And so this means that no matter how far the pedestrian is, you will be able to predict it if your track query is still alive. So the cool thing, as I said, is that there's no need for an extra re-identification head. The bad thing, though, is what I was telling you before about the spatial information, right? This kind of prior that it is embedded in the track query means that you cannot use this for long-term occlusions, because your track query is going to be looking at the bottom left part where the object disappeared. If the object reappears on the top right part of the image, then the track query is looking in the wrong location. So it's very likely that you cannot make that association. So I think TrackFormer and variants of it, so we're not the only ones to come up with a transformer-based tracker, but I think it's a super elegant formulation. It kind of naturally merges detection and tracking into a unique formulation. It's end-to-end trainable. It has really good performance with partial occlusions. As I've said, long occlusions is another story. And it also has a good performance where detectors are weak, right? Because you have all the information coming from the past trajectory, and so you have a good prior on where the object should be. And it obtains state-of-the-art results. I put in between parentheses that you do need some data and you do need some tricks. It is a lot of data and it is a lot of tricks. So if anyone has trained Transformer here, you know that you do need a lot of data. And tricks in the sense of, if you want to know more, I can tell you all about it, but in the sense of, you do need to emphasize those cases that you don't find often in data, which means that there's a lot of data augmentation to do in order to, for example, terminate tracks properly, initiate tracks properly. So there's an art also in training transformers. And as I've said, we're not the only ones to do this, so there are other papers that have come up with a very similar solution. Okay, so usually, I would end the talk here saying transformers are great, They work for tracking. This is awesome. We have end-to-end. But it turns out that even TrackFormer has its own problems, right? As I've said, the biggest problem is that it requires a lot of data, up to the point where mod challenge training data is not enough, and people are training on detection data. Now, the cool thing is that you can train TrackFormer with just 2 frames. You take 1 frame, you perturb it a little bit so that your bounding boxes moved a bit, and you train your TrackFormer with this pair of frames. And so this means that you can actually use training detection data sets for training, which is super useful for mod challenge. But it also means that it takes a while to train this. And it is actually unclear, or shall I say, these methods don't really generalize. For example, if we don't see any of the mod challenge data, we use tons of detection data, really tons of detection data, tons of GPU hours to train this. And still, if we don't see mod challenge data, our performance is going to be a lot worse on the mod challenge test sequences. So it really does depend a lot on data. And this is not always the case for some real applications, right? For mobile robot navigation, for autonomous driving, you need to be a little bit more reactive to changing conditions. And so we were trying to think, okay, how about creating a tracker that generalizes to diverse tracking conditions, to diverse weather conditions, illumination changes, which means that it does not require vast amounts of training data. It does not depend so much on the training data. And it turns out that the solution was where we began, in tracking by detection. So you might have wondered, why is this woman explaining the simple online tracker with the Hungarian matching at the beginning, right? Like, why are you telling me this? This is super outdated. I don't care about Hungarian matching. But it turns out that this is going to be the state-of-the-art tracker if we pay a little bit attention to details, right? So when people were using this type of tracker, it was back in 2015, 16, not much deep learning happening in the tracking community back then. And so the features that the tracker was using were very poor compared to TrackFormer type of features. But if we put in more data, and if we understand what kind of problems are there in this tracker, it turns out that, you know, we can convert it into a state-of-the-art tracker that actually generalizes much better. And the devil is all in the details of how you define the distance between bounded boxes, right? This is the only information that you can play around with. The Hungarian is a fixed algorithm, always gives you the same solution. So the only thing that you can do is define this distance between boxes properly. If you define this properly, then you're going to have a perfect match. Now the question is how to do this, how to define these numbers that we put in there, the distance between the detections and the predictions. And so as I said, the devil is in the details, and how people used to do this is by having, first of all, several new concepts here. One is the memory bank. So I'm just saying this because this is going to be an important part of the tracker that I'm not going to go into too much detail with, but it turns out that the way that you treat active and inactive tracks is very important. By active tracks, I mean the pedestrians that we are following frame by frame. They are visible in all the frames, and so I can obtain a good appearance model. The inactive tracks are the pedestrians that are occluded. Could be that they are occluded, could be that they left the scene, but currently I'm not seeing this pedestrian. And so it turns out that you have to treat these two very, very differently in order to obtain a good and robust tracker. Now, the other thing that we have is how we process the actual current detections, right? You usually extract this appearance model with a CNN or with your favorite architecture. And then what you do is you mix these two sources of information, right? You have the motion coming from the memory bank. You can predict a linear motion, you can compute a Kalman filter, you can use your favorite transformer to predict the motion, and you have the appearance coming from the image. And you have to mix these two in order to put this information then in your matrix and compute your matching. Now, there are three places in which it's key how to actually do things. One is how you combine the motion and appearance. People have been fiddling with this since forever, overfitting to the test set, if I can say. The other place is how we compute the appearance model, how do we adapt this appearance model. And the third one is how do we treat these active and inactive tracks, which, as I said, they have to be treated in a very different way. And by just looking at these three parts and paying attention to these three parts, we come up with what we call the good old Hungarian simple tracker, or GHOST for short. And I do know that the order of the acronym is not correct, but the order doesn't alter the product. So here we are with our GHOST tracker. It's like kind of like coming from the past to haunt you and say, hey, all the learning trackers are worse than me. And I would love to tell you more about this tracker, but I'm only going to focus on one of the three aspects, which is actually how we extract the appearance from the image. Because there's a super simple trick that allows our tracker to generalize to a diverse set of data sets. So how people have been looking at this is they have been saying, I'm going to use re-identification features for mod. And by re-ID features, I mean that you have your separate data set for re-identification, you train your model on re-identification, and then you apply it to multi-object tracking. And if you look at all the trackers that use re-ID, they train it in this particular way. There are some trackers that maybe overfit a little bit to the mod challenge or to whatever sequence they are dealing with, but mostly it's trained on re-identification data sets. And it turns out that the features that you need for re-identification and for mod are completely different. So here we see, for example, we have on the x-axis the rank 1, which is the re-ID metric, and on the y-axis the IDF1, which is the mod metric. And we see that on the bottom right, we have all the best re-ID methods, so all the methods that the re-ID community develops, which are not really great at tracking, right? And we have all the tracking methods, which are quite bad at re-ID, but they're becoming better at tracking in the tracking metric. And so where we want to be is not at the bottom right, but at the top left, where this triangle is. Because we don't care actually about the re-ID metric, right? We care about the tracking metric. And so we cannot just take the best re-ID model out there and plug it into a tracker. This is not going to work. Now, it turns out that after a lot of analysis, we found that the solution is very simple, and it's something that many people are doing in machine learning to transfer networks from one domain to the other, which is just reweighting the batch normalization layers. Now, this is, I'm not saying this is novel at all, right? This is a trick that has been since forever in the machine learning community. But it's interesting how it actually extends to tracking, right? So you take your re-ID network, you look at the detections that you have in the current frame. This is a tracking by detection tracker, so you can look at the detections. You extract the mean and variance of these features, and you reweight your batch normalization layers. That's it. And this is what takes you basically from the triangle here on the left to the triangle up there. So you take the re-ID features and you make them work for tracking. And it turns out that with this and the other three tricks that I've said, we can obtain a state-of-the-art tracker, not only on mod challenge, but on three other benchmarks, BDD, dance track. If you've ever worked on these sequences, you will know that they are widely different. But it turns out that we can track people, which is what we train our re-ID and our tracker for. But we can also track cars. We can track any type of object without retraining the whole thing. And we are state-of-the-art across data sets, but I think the most interesting thing is that we didn't train on a single tracking sequence. We didn't see any of the training data of all those 4 benchmarks, and we're still generalizing, we're still state-of-the-art on those benchmarks. So I think that's quite impressive, right? Because it's a super simple tracker. We use very simple techniques, but we pay attention to details, and we obtain a tracker that can generalize. And I think that this is actually the beauty behind the GHOST tracker. Okay, so just to recap a little bit like what I've been saying, I first started with the tracking by detection paradigm. How can you use graph neural networks for offline tracking, good for labeling problems, for example. I then presented tracking by regression tractor, which is a detector that has been turned into a tracker. It's a good, simple tracker that can handle a handful of known objects. I then moved into tracking by attention or using transformers for an end-to-end solution. I think very elegant, very powerful if you have the data. And finally GHOST, which is the easy, fast, and generalizable, which is good for applications, for example, autonomous driving, where you need to have a lot of adaptations between different scenes. But the bottom message that I want to get through you is that you do need to get cozy with your problem and your data. You need to understand your problem, and nowadays that we're using deep learning, you need to understand your data. And sometimes this gets you much further away than trying to tune the architecture for a specific problem that you don't really understand. So, okay, so I've been, doing tracking people since forever. But I want to talk just for one slide about what I think is next for multi-object tracking, right? Like, why am I excited about multi-object tracking still? And this is when we leave all the detections behind. I've talked about tracking by detection. Do we use detections or not? 1 step, 2 steps. But what about when I don't have a detector? What about the case for open world tracking, right? So this is when I want to analyze videos in which I have classes for which I don't have pre-trained detectors, classes that I've never seen before, right? Imagine your autonomous car that has been trained on cars, on people, on motorbikes, and suddenly a horse appears in the middle. If you have not trained for this particular sequence, you're not going to be able to track it with none of the trackers that I presented. And so I think this is a super interesting line of research where tracking should really take the lead, because if you have just an image of a new object, you cannot say much about it. But if you see this set of points that are moving, this set of pixels that are moving forward, well, now you can start inferring some quality about this object. And just so that you know the scale that I'm talking about, so here on the y-axis we have the number of objects. And mod challenge is this tiny dot in here. We just have one type of object, people. Kitty also has a handful of classes of objects. And the scale that we want to go with is this whole thing. So really tracking any object in any type of scene. So I can say that the open world tracking benchmark is open. So you can already download the data, try it out. We try to define a benchmark for an open problem, which is really hard because by definition, open world is open and benchmarks are closed world. So we try to simulate this open world in a benchmark. Take a look and see what you can do with this open world tracking. I think this is going to be a super excited line of research for the future. And before I finish, I do want to give a shout out to a new project that NVIDIA has here in Barcelona, the NVIDIA. And this is essentially sort of a service that NVIDIA is providing to researchers, but I think it's a really nice thing. So it's already happening in Italy, where I'm based now. And they're also taking it here to Barcelona. And the idea is that, the usual cycle of research, you obtain your funding, you start doing your papers, maybe you buy some compute with this funding. Well, it turns out that NVIDIA provides you with an engineer that is going to help you get the most out of your GPUs, right? And this is really cool because you not only get GPUs and compute power, but you also get actually a person that is working there with you side by side. And so in practice, this can take many forms, but it can go from, helping with the software development, helping with performance, scaling up your problem, running it on large clusters. And what I think is really interesting is that you actually get this person, this engineer, to work with you, right? So you can also learn from each other. So I think this is a really neat, let's say, initiative by NVIDIA. But there are actually 2 people here that are taking on this initiative right there in the middle. So if you want to work with them, just go talk to them and take advantage of finding out what this project is all about. So with this, I want to conclude my talk. Thank you so much for your attention. And if you have any questions, I'll be happy to have a discussion.
Thank you very much, Laura, for your talk. Any question that we might have in the room?
Thank you. It's open? Yeah. Thank you very much for your great, interesting, and clear talk. Very interesting and illustrative. For the, I have a question for your last method, the ghost one. At some moment you said that the devil is in the details, and you commented that it's good to treat separately the active objects and the inactive ones. Could you extend a little bit more on that, on how you treat them separately?
Yes. Maybe I can pull in some slides here. So this all comes, I think this visualization, it's a little bit long to explain, which is why I didn't explain, but I can take the time now. So the idea is that you have your active tracks, which are the ones that you're actively tracking, right? And for this, you can compute great appearance models. A person is not going to change too much the appearance from one frame to the next. And so if we plot, for example, the distance, the re-ID distance, so the appearance distance between two boxes with the same ID, we end up with the pink distribution in here, which needs to be close to 0. 0 is good, 1 is bad. So 0 means that the two boxes are actually the same person, right? So the closer this is to 0, the better. So this is all good. The distance between the detections that are not the same is actually the dark pink one, which is behind this dark yellow one, right? So these are nicely separated, right? Like going to 0, going to 1, which is exactly what we want. So if we were just to use a threshold in here, it would be super easy to separate these two. Now the problem comes with the inactive tracks, right? The inactive that are not the same have roughly the same distribution as the inactive that are the same. But the inactive ones that do belong to the same ID are the ones that are distributed here in this bright yellow, which means that they're all over the place, right? So I could have two detections that belong to the same identity, and that are placed here, so almost close to 1, right? Which means that if I threshold these two distributions, I'm going to get a lot of noise, right? So aside from choosing, So aside from choosing different thresholds between active and inactive, and these thresholds cannot be set by hand, but they have to be learned from data on the fly. Aside from that, I have to get rid somehow of this block here, of all these appearances that should not belong here. And so for this, we actually propose a proxy appearance, which is also not a new idea, but we kind of systematically analyze different types of proxy appearances. So essentially how to better express or how to better model the appearance of an object that has been inactive for a while, which means that we'll change the appearance in the future once it reappears. And so it will be harder to match. Yeah, this is just a bit the overall idea, right?
Good. We're going to be moving into the coffee break because we are bleeding into that time. If there's any more questions for Laura, please make sure to talk to her during the coffee break. Also for the speakers in the next sessions, if they can't stay, just to check the slides and the sound, that would be great. Thank you.
Puedes intentar conectar el teu ordinador.
Sí, sí, algo fácil. Vamos a ver si el HDMI funciona.
El HDMI el tens aquí. I no sé si t'has pogut connectar a la xarxa.
Ni lo he probado. He venido con el tiempo un poco justo. A ver, voy a quitar el VPN. ¿Es importante que me conecte a internet?
Ah, no, és que si
vale.
necessites. Vale, o sigui, podem intentar. L'única vegada, sobretot els Macs, no funciona. Llavors hem de mirar a veure si funciona i si ho tens aquí, quasi que millor. Però si no podem... Si tens el portero aquí, agafa'l i ho provem.
Ahora mismo... O sea, esto debería ocurrir mágicamente, porque mágicamente no está funcionando.
No, ho hem de demanar des d'allà.
Ah, vale. Vale. Prueba la tuya, que viniendo de Microsoft a lo mejor no tienes un Mac. A lo mejor el tuyo funciona directamente.
La idea és deixar el mateix ordinador amb totes les diapositives.
Sí, la idea seria deixar l'ordinador amb les mateixes diapositives. L'únic que si porteu el vostre, podeu mirar la perquè a vegades ja me l'ha enviat i ja tinc algú altre entre mi i es pot.
Vale, i la gent ha enviat diapositives en... Ah, no.
A veure...
Un pen de quin tipus? Ah, no.
Doncs llavors, si m'ho mires a la llum.res@cpunedo.
Vale.
Ahí cada no tiene internet.
Jo prefereixo si em podeu posar aquí, si no...
Sí, jo li estic enviant ahir a les slides i ho tindran tot en el mateix ordinador.
Vale, perfecte. Us ho
Jo.
envio.
Sí. Hola.
Vale, Pedro. She's the chair of this session, so we were making sure that everyone...
Ah, ja.
nos conecta.
Vale. Pues casi mejor presento con este porque este no cabe en el A3. A ver... Sí, dale.
Si voleu buscar el vostre link aquí i el mireu d'obrir.
Vale.
Sí, ja el tinc obert el teu, però sí.
Una vegada vull connectar... Una vegada vull connectar, vale?
Pujo dalt i
Vale.
Una cosa, lo del vídeo que decías es esto de aquí.
Sí, o sigui, els vídeos aquests estan fets a web través perquè no tinc accés a veure'ls i des d'aquest ordinador
Vale,
es veuen.
entonces lo tengo que hacer público o algo así.
Sí, o público o lo compartes a laia.res.
Vale.
I ho pots mirar des d'aquí també.
De momento, no. Bueno, pero parece que ellos
Tiene que darle. Sí.
De momento no hay ninguna sorpresa. ¿Cómo? Son las 10:15. Bueno, muy mal aún. Ay, coño. La conexión es esa, bueno, no te funciona. Yo lo estoy probando ahora.
No, depende de lo que no cabe en el A3, por eso.
¿Y qué hay un HDMI aquí?
Sí, es este.
Pues creo que voy a probar con el mismo.
De momento no. Es que han de primer donar-li allí, però això encara estic aquí esperant. Sí. O sigui, si et fixes, a la pantalla no es veu ni aquest ara mateix.
Bueno, yo voy a aprovechar para el baño.
Vale. Estan fent el cafè. You can use this or your laptop. You can choose.
¿Trabajas aquí en Epic, en Barcelona?
Sí, trabajo en remoto, pero estoy en Barcelona, sí.
¿Con qué tipo de trabajas en Epic?
Estoy trabajando con Ian Matthews.
Con la gente de California.
Bueno, ellos están en Pittsburgh.
Ah, coño, es verdad, sí. Vale. Yo trabajo con Meta en Pittsburgh, pero conozco a gente, pero ninguno de ellos está en Pittsburgh. O sea, ¿no trabajáis con Carsten?
Sí, trabajo con Carsten, él está allí,
Y
en
ahora
California.
se acaba de unir Christoph.
Sí, la semana pasada creo que fue, sí.
Guay, joder, que estáis juntando a la gente.
Sí, somos poquitos, pero estamos distribuidos.
En Madrid hay oficina, pero no hay...
Lo que hay en Madrid es Mediatonic.
Claro.
O sea, Epic compró Mediatonic y tiene la oficina allí de videojuegos. Y también tienen otra cosa aquí en Girona, que compraron de una startup de por aquí en Girona, pero no hay research aquí en España. De researcher en España estoy yo.
Ya. A mí, cuando yo me cambié a Meta también estuve hablando con Carsten y me dije, sí, puedes ir a Madrid. Y, hostia, pero O bueno, yo trabajo también aquí en Meta solo.
Sí. Sus partes buenas y sus partes malas.
Sí. Bueno, yo voy a Pittsburgh una vez cada, o al menos iba. Ahora con las historias estas de los budgets, no sé si le dan a menudo, pero iba cada 2 meses. O sea.
Yo solo he ido una vez en Pittsburgh, fue en verano, pero es verdad que yo estaba haciendo mi internship. Cuando terminé el internship me uní ya de forma oficial y al mes o 2 me fui entonces una semana a Pittsburgh. Porque estuve en SIGGRAPH y luego ya aproveché y me fui para Pittsburgh.
A mí sí que me gusta ir de vez en cuando, como para
El tema es que
ver una energía, yo qué sé, la oficina, algo...
Sí, el tema es que ahora en Pittsburgh, porque están distribuidos, está Ian,
Sí.
Paco y una persona más y ya está nadie más en la oficina. Claro, estamos en California, España.
Coño, o sea, solo hay 2 en Pittsburgh.
Ahora mismo hay 3.
¿Dónde está la oficina en Pittsburgh?
No me sé las calles, pero está...
¿En qué zona? O bueno, da igual.
O sea, si te lo puedo mirar, pero no me acuerdo. O sea, yo fui allí, cogí el hotel al lado.
Déjame aquí.
Mira,
sí.
está... Creo que es downtown, está por downtown. Sí.
Vale. Está cerca entonces de la DM.
Creo que
o sea,
sí,
Pedro
que...
tiene un bar, pero...
Creo que ella me dijo que estaba cerca, sí.
¿El tuyo funciona?
No me había fijado.
Mira si los vídeos y demás.
Sí, ahora vamos a ver el vídeo. Vamos a poner este. Por algún motivo. Sí, ¿no? Sí. Pues ya está.
Vale. Sí, suerte.
Sí. We can move it to put it in
A ver, que parece que funciona, pero tengo que poner los displays... Bueno, espérate, a lo mejor no hace ni falta, un
Crec
momento.
que a la Laura li passava que quan tornava a presentar li sortia.
Sí.
Ahora sí funciona. Se mueven las cosas. Se mueven las cosas, maravilloso.
Tens algun vídeo?
Sí, ahí estaba moviéndose ya. O sea, parece que va.
Tots aneu amb el vostre? Vale, doncs feu.
Ens podes llevar, no?
Has provat a veure si això funciona?
No.
Sembla que han tornat a treure, no? Perdona, però... Vull dir que estic connectada, però...
No funciona. Vale.
No s'està connectant? És culpa meva, és culpa
És
del
de
ordinador.
l'ordinador, que els Macs a vegades no els agafa del tot bé. No sé si potser algú et pot deixar, li comparteixes, o si no tenim aquest ordinador, que no és Mac, però...
Vale.
No sé si és PowerPoint o...
És PowerPoint, prefereixo que sigui un Mac perquè m'asseguro que les transicions... Qui parla abans meu? Perquè el més fàcil és la persona que parli abans meu.
L'Albert.
L'Albert, qui és l'Albert? Tens un Mac, tu? Sí. T'importa que passi la...
Vale. Sí.
I connectem el papel. Sí, d'aquest el problema és que la visualització en presentador, mira com es veu. Sí, se't veu aquí. I llavors...
Me traigo el miento al profesor.
Sí? Sí. Vale. Potser si no ho fas des de Google Slides sí que et funciona. Bueno, provem. Do you want to try?
I saw them here. Okay. This?
Yes. This one?
Yes.
It will be shown like this. Is this fine?
Yeah.
Do you want to check if there's a video, if you can see?
Yeah, I don't really have a video, so I think it's
That's
fine.
perfect.
Yeah, I think it's fine. Okay. Just the title. If we can change the title in the first
Yeah.
page, because people are asking me, but it's fine.
Okay, I'm so
No,
sorry.
it's not your fault, it's mine.
Communication breakdown. Okay, I will go up there and change it.
Yeah, thanks.
And yeah.
So I will wait.
Yeah. Thank you. Has provat la teva presentació?
No, te l'has enviat.
Vale. Compartir amb... Sí, ho pots tenir aquí millor. Era...
Te l'has enviat a l'email.
Ah, l'email. Vale. Aquest no era, oi? Vale, són aquestes i aquestes...
Les podem obrir per mirar això?
Sí.
PowerPoint, però el tema versions i tal.
Es veurà així. Si vols mirar... Ui, ara.
Sí, veiem els GIFs, tal.
Sí, perquè és con PowerPoint, sí. És que si no tens vídeos sí que ens ho podem baixar i...
No, pues que prefiero poner en el...
Vale. El vols posar aquí o no, el de l'Albert?
Yo tampoco tengo PowerPoint y es oculto.
Vale, doncs sí, ho posem aquí. Si amb el... Sí, ho provem. A veure, aquí no sé si hi ha... Vale, USB normal, sí, USB. És que ja no estic acostumada a treballar amb Windows.
Jo tampoc, o sigui que hauré de tenir clar com dir això.
Doncs crec que li dones aquí.
Vale, puc provar que les transicions funcionen.
Sí, tant.
I això amb quin...
Ja la provem el teu, vale? Mira sobretot si tens algun vídeo o algun GIF.
No, no tinc vídeos, però vull mirar que totes les transicions... Bueno, sembla que...
Està tot bé?
Sí. Vale. Però ho poso ja... Bueno, és que de fet ho hauré de... O sigui, el que hauré de fer quan vingui aquí...
És, obres aquests, mires aquí baix i dius, vale, doncs és aquest. Aquest ja... Espera, aquest te'ls tanco perquè el seu no, perquè això... Aquest sí, aquest.
Ah, és el... Vale.
És el segon. Vale?
Hauria de posar el nom davant, potser seria més fàcil.
Sí, si vols, ho podem canviar.
Sí. Bueno, és igual, ja dic. Has de provar aquesta.
Sí.
Pues no, prova la cosa.
Vale, poso Àgata... Uips, Àgata... Vale? Així. Arxivo en uso. Ah, vale, l'he de tancar i tornar a obrir.
Ai, tranquil·la.
Intentar de nuevo. Ara. Ara ja està. Vale. Doncs el tens aquí. Aquí, en el PowerPoint, el segon. Vale. De res. Vale. Doncs té prova aquest. El pen, espera que et faig, te'l trec... Com es fa això aquí? Has vist? Vale, ja està, ja el pots treure. Gràcies, Àgata. Tothom ho fa del seu portàtil, els que ho han provat, menys l'Àgata que no li funcionava el seu. I... Qui més era? A veure... Qui més hi havia? El Víctor, que també ho fa des d'aquí. Sí.
¿Me mueves esto, porfa? Un momento.
Sí, también.
Muchas gracias.
Prova a veure que vagi el següent. Sí. Els que presenteu amb aquest, bueno, recordeu-vos que està aquí, que simplement heu d'agafar i connectar-li l'HTML, vale?
Vale, pues ya está.
en punt bo, això. No sé, yo he conectado este cable, ¿eso que tenías tú conectado?
Sí, sí, era este.
Vale, ¿y ya se tiene que salir o tengo que...?
Yo creo que te tienen que dar permiso desde ahí.
Ah, vale, vale.
Tipo, ahora está el ordenador de ellos y cuando ellos te den permiso se activará.
Vale, estaba probando y como no veo nada estaba un poco... no sé, bueno. Si no, ya vendrá alguien. Gracias.
Ah, no, tranquil·la.
L'únic que l'Eleonora ha canviat ara i ho veus aquí baix també?
Ah, sí. Comença? Sí.
Hello. Good morning. We will proceed with the next session. In this session, we will have 6 talks. Each of them will be 15 minutes. My name is Pedro. I'm from the University of Barcelona in Computer Vision Center. And we have pleasure to begin with the first talk that is presented by Victor Garcia. This talk is entitled Equivariant Diffusion for Molecular Generation in 3D.
Hola. Sorry, I was going to speak in Catalan. Yeah, so this is a work, Equivariant Diffusion for Molecule Generation in 3D. This is a work I did during my PhD at the University of Amsterdam, joint collaboration with Emile Hugeboom and Clement Vignac. And it was supervised by my PhD supervisor, Max Welling. And it's about a generative model for molecule generation in 3D. I will start with a quick motivation on why is it useful to generate molecules in 3D. Then we will talk in the background about denoising, diffusion, and equivariance, and finally we will present the method that we introduced here. So molecule generation has a lot of potential future applications. It's a current work in the intersection of chemistry and artificial intelligence that many companies now are investing with, maybe for the next 5–10 years. And it can really benefit applications like drug discovery, also catalyst design and material discovery for the research of, for example, new catalysts and materials for renewable energy sources, and also for docking problems that play a role in the design of vaccines. So a denoising diffusion model, probably most of you are familiar with it, because this is like the model used in DALI and stable diffusion and all these generative methods for images that are so successful lately. And it consists of 2 processes, a diffusion process and a denoising process. The diffusion process gradually destroys information from an image, as we can see here, by adding Gaussian noise at small time steps. And then we have a denoising process that learns to compute the inverse of this diffusion process. So it learns to remove the noise. So then to generate a sample, it's as simple as just sampling Gaussian noise, and then gradually removing the noise from this sample. Another background concept, equivariance, is actually, well, it's a concept that sometimes can be explained a bit in a complicated way, but it's a very intuitive concept and very simple. And it just means that functions should behave predictably under certain transformations. Like for example, in molecule modeling, if we want to compute the forces of a molecule, they are equivariant to rotations. So this means that, for example, if we compute a function, as we see here, if we compute a function in a, let me see if I can use the laser. Yeah. So if we compute a function in a molecule and then we rotate it, we get the same result than if we first rotate it and we compute the function. So we want to design neural networks that satisfy these symmetry constraints. This also plays a role in when we compute the likelihood of the sample in this generative method, because the probability of the sample doesn't change with respect to rotations, which is what we will expect with molecules. The closest related works we had before this work was GeoDiff, which is a paper that will generate the conformation of a molecule. Those are the atom coordinates given the molecules, so they were not generating new molecules, but just generating the positions given the graph of a molecule. And then equivariant normalizing flows, that this is a prior work that we did the same authors of this paper, and it's a very similar method, but instead of diffusion, I was using a normalizing flows, and it resulted that diffusion provided much better results than normalizing flows for this task, and especially because of the equivariant constraints that we want to input into the neural network. So what we present is a diffusion model that for molecules that it's a diffusion process to destroy the information, then it learns a denoising process to generate, and it handles both continuous and discrete data. Continuous will be the atom types, and discrete data will be continuous will be the atom coordinates, and discrete data will be the atom types. So this will be the diffusion process. We just take a molecule from our data set, and then we gradually add noise. This noise is equivariant to rotations and invariant to translations until the information is lost, and we end up with a Gaussian distribution. This noise is both applied to the atom coordinates and to the atom types, as we can see in the image. There is a trick in diffusion models that's very useful at training, and is that when you gradually add Gaussian noise, the sum of Gaussian noise, the sum of different Gaussian variables results in another Gaussian distribution with higher variance. So we can sample any given time step into this diffusion process by just adding noise with a higher variance. This is a property that's then useful for training. To generate for the denoising process, we just learn the inverse of this diffusion process. So we start from Gaussian noise, and then we remove the noise. And the inverse of this diffusion process can analytically be shown to be also a Gaussian distribution, with the difference that in this case, we don't know the mean of this Gaussian distribution, and this is what we learn with a neural network. So we're gonna train a neural network that learns to shift the mean of this Gaussian distribution from this noise towards the distribution of the data in which we are training on. So the optimization works in the following way. Like now we have defined the diffusion and the denoising process, so how do we train this model? How do we train this denoising process given the diffusion process? So it works in the following way. We first sample a molecule, and then we gradually, we add some noise into this given time step t that we can sample from. And then once we have this noisy molecule that we added the noise in both coordinates and atom types, we input this noisy molecule into a neural network, and then this neural network is going to learn to predict the noise. So the training is actually very simple because we just have a neural network that takes a noisy sample, and then it predicts what's the noise that we added to this sample. And this is the whole objective. The derivation of this objective is a bit more complicated, but it results into this very simple loss. And then we can use this neural network to predict the mean of this denoising distribution that we shown before. And it just, we can show analytically how, in the paper is shown how this neural network is used to predict the mean of this distribution. In order to deal with both coordinates, continuous coordinates and discrete data, there are some papers that work in diffusion for discrete data and different methods that have been tried. But we chose to directly use the same method and for the continuous data, just adding Gaussian noise too. And it resulted also, maybe with some tricks, but it resulted in also very good performance and then a very simple method. And in order to compute the likelihood of in order to compute the likelihood with discrete data, since we are dequantizing, we provide the analysis of that in the paper. But in order to train the generative method, it is as simple as just adding Gaussian noise to the discrete data. So the first step will be just like a dequantization step where we map from discrete to continuous, and then by just adding like more Gaussian noise, everything. When we diffuse, discrete values converge both to just a Gaussian distribution in the with zero mean. One thing that was important is that the noise distribution, it really plays a very important role in diffusion, and since we are playing with two variables, continuous and discrete, the trade-off in the amount of noise we put in one or the other is very important. There is a hyperparameter to tune. This is the one that we have here, 0.25, for the one-hot encoding. And this actually improved the stability of the generated molecules from 47% to 82%. So it's a it's just a hyperparameter, but this one was very important, and it plays with the trade-off in the noise schedule. So these will be the results compared to existing methods. The first is the equivariant normalizing flow. We measure the atom stability and molecule stability. This is a measure from chemistry that it has to do with if the number of bonds is equivalent to the number of, to the valence of the atom, and it measures if these molecules are likely to exist or not. So we have that the equivariant normalizing flow had a very small molecule stability. Then there is autoregressive method that was like the state of the art to the moment, GISHNet. And then the other two are variants of our method with a network that is not equivariant. And those ones, the one that uses data augmentation already outperforms the autoregressive methods. And then we see that the equivariant one outperforms previous models. And yeah, I see I'm almost out of time. So yeah, just to mention, we also use this for conditional generation on a property. So we generate molecules with the property that we want. And then also there is a future paper in this one I was an advisor where we use this generative method condition on fragments, so we can condition the generation of a linker given a protein pocket. That will be something that in large scale in the future will be useful for vaccine design. So yes, these will be the conclusions. We presented a diffusion model to generate molecules in 3D. It has better performance than existing methods. And it has promising results, especially if we scale it to larger data. And some promising future directions will be applying it to large-scale docking problems or also diffusion models for molecular dynamics. That is something that we didn't do in this paper, but it's something that we're working on now, and I think it's a promising direction too. Thank you.
Thank you. Thank you very much. Any questions? Maybe to begin, can you explain a little bit for people that are not working in your topic, what validation, what is the procedure of validation? What data sets do you have and what measures you use and what is the procedure?
Yes, so well, we used QM9 and GeomDrags dataset. Those are two molecular datasets that maybe is more a bit like, QM9 is like the MNIST of chemistry. It's very simple, but it's useful to try the first algorithms. And for evaluation, well, generative methods sometimes we'll know that it's a bit tricky to evaluate. We can evaluate like the likelihood and the validation partition, or we can obtain different metrics. So in the end, we use some metrics from the literature, like the one of the molecular and atom stability, also the novelty of the generated samples, and the uniqueness of the, like how, let's say, how many molecules of the generated ones are repeated. So we use some metrics that are used in the literature to compare to them.
Question? Yes, please.
Hello, very nice talk. Thank you so much. I was wondering, what do you mean by adding equivariant Gaussian noise? No, because I understand that at some point you need to have a model which is invariant to these rotations, equivariant at least, no? Can you develop a little bit further on that?
Yes, so yeah, we're using an equivariant network. Well, let's say Gaussian noise, when we have independent, it's independently sampled for each component, it's already equivariant to rotations as a distribution. And if we center them into zero, it's also invariant to translations. And then the trick, maybe more than in the diffusion, is in the denoising process, where the network has to be equivariant. And there, well, like it's just the choice of the architecture we use. And in this one, we use an equivariant graph neural network, which is it's a model that actually it's from a paper that the same authors of this paper that we designed maybe a year before this paper. And the goal actually was to use it for generative methods like this.
Okay, thank you.
Thank you. Thank you very much. Thank you. We continue with the second talk. The second talk will be presented by Eleonora Gualdoni, and it is entitled Communication Breakdown on the Long Mutual Intelligibility Between Human and Neural Captioning. Welcome.
Hi, I'm Eleonora, and I'm a PhD student in Università Pompeu Fabra in the Computational Linguistics and Linguistic Theory group. And I'm going to present this work that is a joint project with my colleagues Roberto Dessì, Francesca Franzon, Gemma Boleda, and Marco Baroni. So the motivation behind our work is that current multimodal models have achieved impressive results in many tasks. In particular, we know about visual question answering, image captioning, these kind of things. However, there is an however, that is that they have poor performances in caption-based image retrieval when we have highly contextual distractors. And we're going to see what this means in a second. So the images that you are seeing here come from this dataset that is called image code. And this dataset contains sets of 10 images that are extracted from videos. So these are video frames that are really similar to each other. And you can see that one of the images has a green frame around it, and this is what we call the target image. And then we have other images with red frames. These are the distractors. So caption-based image retrieval is the task of guessing which is the target based on a description. And this dataset comes with human captions. So humans have been asked to give a description to the target. And we can see that for this case, humans chose to say no bridesmaid visible at all. So humans are asked to give a description for the target, looking at the distractors, making sure that the description is enough to understand which is the target, without mentioning explicitly the distractors. And we can see that what humans do is to use a like complex structure, saying something like no bridesmaid, so something that is not super easy to understand for a model because it's a negation, and also implies that you understand that the girl with the blue dress is a bridesmaid and that she's moving and she's going away. So it's a complex strategy. We can see another example here. So what humans do to describe the image with the green frame is both hands on the piece of bread closest to the person. So again, something that requires some complex understanding of the entire set. So what neural models have been tested to do was to take the set of images. So you have to imagine that normally these images are 10, so chance level is at 10%, but I'm just displaying 4. And then models have been given the caption produced by human, and they had to guess which the target was. So this is a complex task, as we were saying, because the set is really hard, and the descriptions that humans produce are really complex for a model. The neural retrieval usually is something like a clip encoder, for example. So clip is a multimodal model that learns to process images and text, and in particular, it maps visual information and textual information to the same space, and this makes it really good in guessing which are the captions associated to images and vice versa. However, clip seems to fail in this task. So in our work, we wanted to substitute the human and put a neural model in producing the captions. So the idea is that maybe captions produced by another neural model are better for a neural retriever, that is the model that has to guess. And for example, what we're going to do here is to use ClipCap. ClipCap is an off-the-shelf architecture. We take it as it is, and it is based on clip, so it processes visual information with clip, and then it maps it to the embeddings of GPT-2. So this is a way to kickstart the generation of a caption. So what we're doing basically is to substitute the human caption with a caption that is produced by a neural model. Hopefully, this caption will be more understandable by the other model that has to do the retriever task. So the research questions here are mainly 3. So how do neural captions perform compared to human-generated ones? Are they linguistically different? And do humans and models focus on the same things when they are describing the target? So in short, the result is that neural captions seem to work better than human captions for a neural retriever. You can see that 22.3, that was the best result reported in literature, achieved with neural captions, with chance at 10% again. So we can see that using neural captions instead of human ones already improves the performance of the neural retriever. And then we can check how the captions look. So you can see here 2 cases. I just put one distractor. And if we go to the panel on the left, we can see that the human said something like the gray object is not touching any of the text on the bottom. The woman's left hand is behind the first 2 words of the text. So something really complicated. While the neural captioner said, I'm playing with a prong on a yellow toothbrush. So something really simple and probably not super clear, super transparent for a human. And if we go to the right panel, we see that the human said the last 3 letters of the text on the left are still visible. So again, a complex information. While the neural captioner said a large room filled with chairs and chairs. And apparently this worked, because the neural retriever managed to solve the task. So analyzing the captions, what we see is that neural captions are generally shorter. And humans use more function words, so again, a more complex syntactic structure, while neural captioner use more content words. And we can say that neural captions seem somehow focused on describing what's in the picture for another neural retriever, but definitely they are not discriminative. So it looks like they couldn't work, but they actually work somehow better than the human captions. So to understand why we have this pattern, and if neural captions are really discriminative, we designed another small experiment. In this case, we decided to remove the distractors that are farthest away from the target. This is because it may be that the captions that the neural model produces are good to tell apart the target from the distractors that are farthest away, so the most different ones, but maybe they're not enough to distinguish between the target and the closest distractors. So what we're going to do is to only consider the 2 closest distractors to the target. So in this case, chance becomes 33%. Well, we can see that also in this setup, the neural captions work better than chance. So we got a 48.7, so it's way better than chance. And the second test that we did was to look at neural captions for really similar targets. This is because for how the dataset is built, the same set of images could appear twice in the game with the target being a different image in each trial. So in this case, what we can see is the description for the target in the green frame, that is, a dog is playing with a prong on a yellow toothbrush. And then we can see what happens when the target is actually this one. And we can see that the description here is a person holding a water bottle with a dog in it. So we can actually notice that the neural model is leveraging different information for the 2 images, even if they look really similar to us. And the same we did with this other set, for example. Here, for the image with the green frame, we have a large room filled with chairs and chairs. But when the target is this one, we get a picture of a kitchen with a bunch of televisions in it. And this seemed to work, again, for the neural model. So the final step of this project was to test human retrievers on this same task. So we ran an experiment on Amazon Mechanical Turk, and we selected the sets where the neural retriever had guessed the target and the same amount of sets where actually the retriever had missed the target. So we have balanced sets. And we asked humans to perform the same task with both the human caption and the neural generated caption. And what we get is exactly the reverse pattern. So we can see that humans seem to like human captions because they achieve 54% accuracy, and baseline is again 10. And neural captions seem to like more neural captions. On the other side, both humans and neural models seem to be close to chance when they have to perform the task with captions generated by the non-matching sender. So for humans, the neural one, and for neural models, the human caption. So in conclusion, we think that purely natural languages seem to be a suboptimal tool when we want to interact with state-of-the-art multimodal models. This is actually because neural languages are complex and fully transparent for us, but they can be hard to process for a model that does not think as humans think. On the other side, the language that machines like is not transparent for us, so we cannot really understand what neural models are telling each other. So the direction of further work is to understand better the current processing skills of neural models to design better communication protocols between humans and machines. And I thank you for your attention.
Thank you. Very nice work. Questions? Do you think that in the future there should be some kind of collaboration between human and robot?
I think we hope so. I mean, yeah, I think that being able to interact better with a machine is useful for many tasks. We're seeing in these days this ChatGPT, and everyone is talking about that. And maybe being able to use a language with these models that is better for them to answer in the proper way is a direction for future work for all of us. Yeah, instead of using this complex natural language that maybe doesn't help machines so much. Yeah.
Okay. Yes, please.
Yeah, thanks very much for the presentation. So I had a question. I was a bit confused about the difference between the neural and the human captions, because it seems that the human captions were actually describing how that image is different from the whole set, yeah. Right? Whereas the GPT-generated ones were a description of the scene, right?
Yes. So. Yes. So what you are saying is true. In our setup, the sender, so this model that describes the target, is not looking at the distractor. So we took this out of the shelf model. So it was only looking for its architecture to the target. And even if it was not looking at the distractors, the captions were better for the retriever than the humans ones that were actually considering the difference between the target and the distractor. But what you're saying is actually a direction for future work. So the idea to align more this setup to the setup that humans have is actually something that will make the comparison more fair. Yeah.
What about the variability? That is, how do you manage, for example, when you speak about human, different humans would say different things, right?
Yeah, it's true.
Yeah, so how will we manage this variability?
Yeah, so in this case, I don't think we took that thing into account. Maybe, well, one way to manage the variability in human generated captions would be to have evaluation protocols that take that into account. So yeah, that's a thing. But in this case, there was only one caption that's a limited setup as well, yeah.
Yeah, so we don't know if this is the right one.
Yeah,
right?
exactly.
Okay, do we have any other questions? If not, probably you will be approached in the break. Thank you very much again. Okay. We go with the next talk. The next talk will be presented by Pedro Ramoneda, and it is entitled Score Difficulty Analysis for Piano Performance Education Based on Fingering.
Okay, hi everyone, thank you to be here. My name is Pedro Ramoneda, and I am a PhD student at Music Technology Group. I am researching about performance difficulty. In other words, the skills or the effort that a musician requires in order to play a music work, which may be used, as you can imagine, in music education recommendation and retrieval. In the first year of the PhD, we have presented these 2 papers. In the ICASSP paper, we presented a first approach in order to do score difficulty analysis. And in the second paper, we advanced in the state-of-the-art of automatic piano fingering, which is very important for the former one. Do you know that also millions of music scores are freely available on the internet in recent years? The diversity in music education repertory has not increased nothing in the last 200 years ago. Everybody plays the same music works. For example, everybody plays the same music, the same classical sonatas of Haydn, Mozart, or Beethoven, but in the classical era, there were a lot of composers. And this is not helpful. It is not helpful when music teachers and students explore the collections because, well, the main websites and online music libraries have categories that are not useful from a pedagogical perspective. That is why we want to understand music difficulty to allow students and teachers to explore large collections. The lack of diversity is particularly high in repertory is historically underrepresented. For example, women composers. Most of you have here pieces from Mozart, Chopin, or Debussy, but probably most of you have not heard about Cécile Seminat, Lulu Boulanger, or Clara Schumann. But the thing is that there are thousands of classical composers that are never played. And this is because music education has a very strong oral component, which produce most teachers only assign to their students pieces that they already know. And it's very difficult to explore the large collections of classical music. Moreover, my major motivation is, as piano teacher, usually students ask you, can I play this piece? And the typical answer is, no, maybe in 5 years you can play that. We think that if the students have a more implication in the election of their curriculum, this will increase their motivation. Moreover, there is a lack of formal definition of performance difficulty from musicology. From a technology perspective, performance difficulty analysis is a very unexplored topic. Moreover, it is a very difficult task because difficulty is personalized for each music student, that is subjectivity, and moreover, the information is in a lot of dimensions, no? And another issue is the few data. No data set was available before our ICASSP paper. And moreover, this is very important for music technology because it can allow automatic composition constrained to music education purposes, and also it may allow curriculum learning in other piano music information retrieval tasks. As I have mentioned, music can be represented in music in multiple modalities. However, in order to understand better the difficulty, we have focused our first efforts in symbolic scores. In particular, in format music XML. It's a XML-like format where all the information of the score is semantically accessible. To that extent, we transcribe one of the greatest pedagogical works of our piano, Microcosmos of Bela Bartok, composed of 150 pieces by the composers in order to teach their sons to play piano, and is ordered progressively in difficulty. Pianists learn to move fingers and hands physically progressively. Therefore, knowing the potential fingering and hand movements, we may characterize difficulty. Music performance is one of the most sophisticated human motions. It depends on the planning and coordination of appropriate hand and finger movements. The movements of fingers, and therefore hands, are denoted in the scores by piano fingering labels, but most of the labels are not written in the music score. Pianists must learn to choose the order of fingerings to play the piano keys, because it's a creative and highly individualized task. Automatic piano fingering tasks retrieve the finger labels corresponding to each note of the score. Oh, I'm sorry. Well, that is it. The thing, I cannot play the video. One moment. Well, the idea is that from each node, one finger label can be retrieved with automatic piano fingering. Then from representations pedagogically motivated on piano technique and fingering, we propose two baselines that can classify difficulty at the global level and give the students local feedback. In the first model, we work with windows or score segments in two levels of classification. First, we classify the windows in a noisy label scenario. Second, we classify the full piece based on the output of the first step. It is a noisy label scenario because if a piece is not of one level, that does not imply that the segments are of that level. That means that not all the parts of the piece have the same difficulty. In the second approach, we work on the entire piece length. The model is based on GRUs with attention mechanism. From both, local feedback can be extracted, as you can see here. With an evaluation of the classification and ranking potential of the task, we saw that the features based on fingering outperform the features based on only the score. However, our data set is a very close scenario because, well, it's only compositions from one composer, no? And other drawback was that we detected that some pieces, the automatic piano fingering algorithms in some pieces were underperforming. As I have mentioned, we extract the feedback for the first stage in order to understand a bit the behavior of the algorithm and give some type of feedback to the music and teachers. Consequently, we decided to focus in automatic piano fingering. Also, music scores do not contain all the fingers and hand movements or as other technical elements, sometimes present partial annotations, as you can see. Then the most difficult parts are annotated. Then we think, why we don't model this as a semi-supervised task, and then we fine-tune to the fully annotation. And moreover, the existing data set of fully annotations is multi-annotated, and then we can understand the agreement of the annotators. Then we created a thumbset data set, which is like 50 times bigger than the existing one. As part of our methodology, and thanks to expanding the domain in the new data set, we propose two autoregressive networks. Both have the same encoder-decoder type of architecture, and the first one have the same representation of the previous state of the art, only using well, this one, no, but it's autoregressive because with the previous few data was not possible to train autoregressive networks. And in the second one, we use graph neural networks in order to have a very good representation of polyphony. Polyphony representation is an open challenge in most of music technology machine learning tasks. Finally, we saw that, well, basically we can outperform the previous state of the art, and in particular, we have reduced to the half the error compared with the human agreement. In this example, we saw how autoregressive and polyphony representation are better modeled with our proposal. However, we have to still working on this topic. In the present, we have created a bigger data set than Microcosmos in order to have a bit more diverse and real scenario. We are exploring other dimensions of music besides of technique, and moreover, we are working with the SMUC department in order to establish the term of difficulty from a more musicology perspective. In the future, we want to expand the research to real-life formats as PDF or audio. And moreover, we want to create interfaces in order to explore better the music education corpora. And also, we want to create systems with the outcomes in order to reduce the difficulty of some parts of the certain music passages. And finally, everything is open science in order to promote the research. Thank you so much.
Thank you. Thank you. questions? What are the conclusions? I didn't understand.
Yeah, what are the conclusions? Yeah, the conclusions are that the conclusions probably are that...
Yeah.
The conclusions are that probably the most important thing that we have to do now is to define well the term of difficulty, because everybody in the music education community use the term in a difficult way, no? And if we try to understand how humans standardize the concept of difficulty, we can try to understand the parts that are objective, no? Because, well, of course, pieces are subjective for... the difficulty of a piece is subjective, no? But in general terms, there are some boundaries that are objective. And we have to understand well that boundaries in order to advance our research.
Okay. Do you need to be able to play piano in order to do such a work?
Yeah, I thought that in the previous version of this of these slides, I was playing piano. However, I read like 2 days ago that we only have 10 minutes, then I have to add the slides.
Okay. Any other questions? Today, audience is silent.
Thank you for the nice talk. Just one question about the fingering generation. Do you have to somehow account for the fact that there might be alternative fingerings that are just as good as the...
I am not understanding, I'm sorry. Can you repeat?
The question is regarding fingering and the potential to have alternate fingerings that are also just as good as another one, and how you account for that in your modeling.
I can tell in Catalan if you want, or Spanish. So like he's saying like there are like to produce a specific sound with the piano, you can produce it like with a specific fingering, or like with another one that are equivalent. So
depends of the pianist, no, and depends of the size of the hand, and depends in a lot of things, of course. The thing is that there is an agreement between the piano, for example, in the previous data set about piano fingering, was an agreement between annotators of 70%. Then most of the notes are fingered in the same way. But we have to say that this is biased because it was a data set very focused on professional performance, not in music education. Probably if a little kid plays the piece, the finger is so different. Then of course, the thing is that there are multiple available fingerings, and that's why I don't mention here, but from the autoregressive decoder, we can extract the top best fingers. However, the drawback is, and we are doing that, of course, and we are retrieving like the 6 best fingers, because I wanted to use that as that augmentation of the difficulty classification. But however, the problem is that the agreement between the top fingerings retrieved are very, very similar. The agreement between them is like 95%, then it's not so useful.
Thank you.
Thank you very much. Thank you. We continue. Next talk. Next talk will be presented by Javier Romero, and it is about AutoAvatar, autoregressive neural fields for dynamic avatar modeling.
Okay. So, I'm Javier Romero. I'll be presenting this paper called AutoAvatar. This was work done in Sikian by internships with us in Reality Labs in Meta. So, what is the problem? Here what we want is to transform a sequence of these raw scans here in gray, although the color is a little bit funny in this screen. These raw scans in gray, which are captured from photometric scans. This is basically 200 cameras or a few cameras looking at the center and reconstructing geometry, which is unregistered, is highly dimensional, but very rich, together with very basic registrations for those. That means that those surfaces in blue are really just created from a few parameters that represent the pose and the shape of the person, but those are not really representing accurately the surfaces that we are seeing in there. And we want to convert that into rich representations like the ones on the right, on the left, which contain all the detail, all the soft tissue deformation, but that are parameterizable with a low dimensional representation, like pose and shape. So basically, transforming the things in the blue, in the left, to the ones on the right, thanks to the data that we have in this rich but unregistered, unstructured way. This is not a new problem, and as we've seen in previous talks from Pedro and from Laura, autoregressive models are one of the default ways of dealing with these temporal sequences, right? This is old work that we did a few years ago, in which we are taking rich registrations and creating an autoregressive model that allows us to parameterize these motions. Another one, more recent, is Soft Simple from Igor Santesteban and Dan Casas, which does a similar work, updated in a few ways, nicer. Both these papers have one limitation, which is that they are based on mesh-based representations. Those have a constant topology. You cannot, it's difficult to add clothes which change topology when you open your jacket or so. And they have very specific resolution, so it's difficult to encode details in there sometimes. On the other side, people have attacked this problem of resolution and constant topology by using implicit surfaces. These implicit surfaces basically are, means that you are training a neural network to evaluate whether one point in space belongs to the surface or how far from the surface is. So changing to the deep neural world where you can work with functions in order to evaluate these surfaces. And there are works like this, like Neural, GIF, again, this is from Gerard's group, SkinningNet from Michael's group, and Shunsuke, and Snarf as well. All these, as you see, there's lots of clothes in there that allow you to change topology. You can potentially have very good resolutions as well in there. But there is a problem. They are not autoregressive. Sometimes they use history of poses or history of parameters as input, but it's difficult to encode dynamics in there. So this work, AutoAvatar, is about this main idea, which is how or can we create an autoregressive model based on implicit surfaces, not based on meshes. And if you pose this question to a new student, they think, well, I mean, sure, we can. We take our meshes or our poses on the top, P, implicit surfaces, S, and I'll put a neural network on this, and we'll get some implicit surface in between, on the left, and we can, in the next frame, we can circle that back to the input and obtain the new frames in an autoregressive manner. This is not trivial because, I mean, first, if you, even before thinking about implicit surfaces, if you want to represent these volumes, you would have to think about voxels, which have like cubic complexity. You have lots of parameters in there. Modeling autoregressive models with so many parameters is tricky. If you think about implicit surfaces, suddenly your dimensionality could be potentially smaller, but those are functions. So how do you feed a function to a neural network and extract a function on the other side and feed it back? That's also kind of conceptually weird. So we'll change the representation. We'll do a representation tricking here. And what we do is that we take our parameters, which are our simple poses, P, and the other input, which is our implicit surface from the last frame. So basically here, pose and implicit surface. The pose from our simple model entails a surface which has points, right? But this is, again, a very coarse representation. This doesn't contain the details or the dynamics of soft tissue deformation. With those points, however, we can relate those parameters to the implicit surface. And the trick that we are doing here is that with those points, we can measure what is the height or the distance from those points to the implicit surface. And in that way, we're transforming this implicit surface, which is a function in 3D, to a set of, or an array of signed heights, which basically, if our meshing here has, let's say, 3,000 points, we have 3,000 scalars, which suddenly sounds much more like a representation that our networks will be able to deal with. Okay, so we have some potential representation in there. We need to solve the representation on the other side. So on the other side, thinking about how neural networks work these days, which sometimes mirror the representation in the inputs and the outputs, we can think that we'll have also something like 3,000 points or dimensions in there with features instead of heights. So we've transformed the heights into features. And that representation in 3D will allow us to take a query point, because since this is a function to evaluate on a particular 3D point, you want to know what is the distance to the surface, and relate that to the feature. How do we relate that? The simplest thing that we can do with that query point in orange in here to relate it to the body is that we compute what is the nearest neighbor in the mesh. Here would be VI, and take the feature from there. So that would be one way in which we take information from the mesh related to the query and put it afterwards to a neural network, PointNet, for example, to transform it into a signed distance function. For that query point, it will give you the distance to the reach surface that you want to represent. That is definitely not enough, in part because, I mean, it's a signed distance function. Your closest points can have lots of different distances for the same point, so you need at least to include as well the distance to the point. So that sounded like it could work. But in order to make it good, you have to add a couple more tricks in here, which is, one of them is introducing the orientation of the vector between the closest point vector to the normal, to the surface. And finally, for areas in which you have nearest neighbors that can change rapidly, like between your legs or between the head and the arm, there can be points in which your closest point could be the head or the arm by changing very little the 3D point. That would make it very unstable. So instead of using only one nearest neighbor, we will use multiple of them. So we take the features that come from all these points. We also take the distances and the cosine of that angle that I mentioned before. All that information is put through PointNet, and that PointNet will be trained together with the rest of the networks that I mentioned before in order to give you the signed distance, the distance from the query to that rich surface that we want to extract. And when we put this together, this is almost, I mean, this can actually work, but in order to make it even a little bit better, there is one last trick that we'll play in here, which is that instead of working directly with these signed heights, we'll be working in 2D space, because as you know, I mean, the world of deep learning in images has always, I mean, has been around for a little bit longer than 3D neural networks, and tends to work in some contexts a little bit better. So we're transforming these signed heights, which, as a reminder, those are 6,000 numbers depicting the distance to the surface. We are basically unwrapping that into a UV space. It basically is just a change that those 6,000 numbers will lie on a plane, and by that we'll be able to process that as an image instead of an array, and we'll be able to use networks like UNet. We do that for the current frame and the previous frames, because we want to use a history of frames to reason in an easier way about dynamics. And we are adding also some other data in here. One is that we are adding information about the pose. This is basically just taking the joint angles of each part and representing it also in that UV space in 2D. And we're using also the derivatives of that, meaning the difference between current frame and the previous frame. So all these are incremental changes that are making things just a little bit better. There is lots of ablation studies in the paper if you want to learn more about that. And that is the system, basically. As I said, taking the poses, transforming into height values, you unwrap them, add the pose information, pass them through a unit. Oh, I forgot to say that once you have it in 2D, you can extract the 3D again because you know the position of the UV in the UV map that represents that particular point. You process that, you get features in 3D that you can query with nearest neighbors, transform that with PointNet, and you get your sign distance function that you can feedback to the network and go to the next frame. Okay, so that's the space. How that's the system. How does it work? Well, there are quantitative studies in the paper. I'll mention here a couple things in terms of baselines. We have basically different sets of inputs that we can use. In here I'm using, for example, the non-autoregressive ones, the ones that are just getting one frame without using the output of the system to infer the input, and using different inputs like directly only the pose, or temporal convolutions on the pose, or the pose and the derivative of the pose. Also, SNARF is a state-of-the-art method that lies in that space. In terms of autoregressive, what we did in order to have some ablation study is to change our height representation, but by embeddings that are either global or local. And the performance here depends on one critical factor, which is the rollout. How many frames will you predict given that you're feeding your own answer to the input? When we say here 1 is that we had ground truth as input and we predict the next frame only. When we say 8, it's that I have ground truth, I predict one frame, I input that frame again and predict it again and again. So when we have short rollouts, our method is the one that performs best. When we have long rollouts, the problem is that suddenly those errors accumulate, and methods that are predicting meshes or representations, surfaces that are close to the average, close to non-dynamic behavior, tends to work better. And this is the same both for an interpolation set in which the sequences are very similar to the ones that we've used in the training set, and an extrapolation set in which those are completely different. This is explained better in terms of examples. So here we see one of those systems, the global embedding that was working best in the long rollout. As we see, the dynamic behavior of the belly, for example, here is much more subtle. It's closer to a method that doesn't have any dynamic behavior, as simple, than ours, which has more fluffiness and dynamic behavior in there. So it's because it's more conservative, predicting things that are closer to static. If we see the other method that was performing well on long rollouts, the one that is non-autoregressive and using pose and the derivative of pose, we see the same thing, very static behavior in the dorsal region. And when we compare with state-of-the-art systems like SNARF, SNARF has lots of artifacts in there. Again, it's a non-autoregressive system. It's expected to not work great. Finally, there is another system, the one that I mentioned from Igor Santesteban and Dan Casas, SoftSimple, which uses very rich registrations as inputs. Instead of using these very coarse ones that come from parameters, they use very good registrations to train their models. And we didn't expect it to work. We didn't expect our system to work better than theirs because we have less information in the input. But in reality, it tends to work a little bit better. It's comparable, just a little bit better, which is already a success that it's comparable. And when we compare the system, SoftSimple and ours behave relatively similarly. Ours has a little bit more detail in certain regions, also has a few more artifacts here and there, but it's comparable with a system that uses privileged information, which is great. And oh yeah, last thing. I have a confession to make. When we started working on this, we wanted to make it work in clothes because one of the powers of implicit representations is this thing that I mentioned that is topology agnostic. You can have a jacket and open your jacket, close your jacket, it's fine. It doesn't require a particular connection between the vertices that meshes have. So it was the perfect place to showcase this work. We tried making it work with clothes. It didn't work nearly as well. The deformations of clothes are substantially more complex than flesh. In the end, you have a variety of materials, and the motion is a little bit trickier. So this remains as future work. Right now, this system doesn't work with clothes, but I think there's an opportunity here to work on harder data sets with these autoregressive implicit deformation, implicit surfaces models. And now I think that's it. Thank you for your attention.
Thank you. Yeah. I also will ask for a very short conclusion, please. What is the conclusion of your work?
Well,
in a sentence.
There is a lot to research still in implicit surfaces. It's a hard problem, so it's not solved. Lots of work to do.
Too short. Any question? How do you validate your technique?
Validation is very hard. I mean, you can have some quantitative evaluations in there, but they are always limited because long rollouts is obviously what you want to have, dynamic behavior that shows throughout the sequence, but since errors accumulate, it's very difficult, and it's very difficult to compare that with ground truth. Suddenly you have sequences that look realistic, but they have deviated because at some point you regress something that was a few millimeters different, and the behavior is similar, but it's not exactly in place. So here we do a mixture of some quantitative evaluation, being clear about where does it work quantitatively and what not, and then quantitative and qualitatively showing that at least visually the behavior is better. I've seen some in similar problems. I've seen now some development of features that tend to work similarly to how it works with images, VGG, perceptual metrics, or perceptual features in there. People are starting to work on perceptual features for 3D that says, well, this thing that is dynamic doesn't look dynamic according to these features, so that's also bad. But there's still a lot of work to do as well in there in validation of these works.
Okay.
Okay.
Questions?
I have a question here. Thanks for the presentation. It looks interesting. I just have a question regarding the minimum number of the frames that needed to train a model. And the second thing, how long the training take to have a complete model or a good model shape. And the third thing, how we represent the shapes, how we can reuse these models later. And the fourth thing, sorry, I'm asking a lot of questions. The fourth thing that I'm looking for is that the ideal metric to compute the error rate that you have. Okay, thanks.
Okay, so I'll answer the easy, hard ones first. The ideal metric, still, as I said, it's not very clear right now because evaluating these dynamic behaviors is tricky to do numerically. Comparisons with ground, I mean, you can have ground truth, but error accumulate, and I haven't seen a good solution yet. Second easy one was, how long does it take to train? It's easy because I cannot remember exactly. It was taking long, but I cannot remember exactly. Then the first question was about how many frames do you need? It's not too long. In here, I think we used the dynamic Faust data set, which has lots of frames. I think it's something like 100,000 frames or so. And we didn't use all of it. Typically, we were training on a subset of sequences and training and testing either on the same sequence but shifted by some frames or different ones. So it's not prohibitive in terms of the data sets that are out there. And fourth was application or something like that, or what is the shape representation?
And the long of the training, I think the second question.
Sorry, what?
How long the training takes?
Yeah, but I said I cannot remember how long it takes. It takes long, yeah.
It takes a day?
Sorry?
It takes around a day or something like that?
I think it's a day, a couple of days, yes, something like that.
Okay, just a last question about the camera poses estimation. these information are already given to the algorithm, or you have some algorithm to
sorry, can you repeat?
For the camera poses estimation. So do you have an algorithm to estimate these camera poses?
For the pose estimation?
For the camera. So you have the object and you have a camera, right? Camera location or poses, I think.
I didn't get it. You have a rotation.
So we have a scene and we have a camera.
Yep.
So I think in the 3D we just have.
So the way it works. So the data, the input is data coming from a 3D scanner, photogrammetry scanner, which takes like something like, depending on the system, from 30 to 200 photos at the same time, and it is basically triangulated every point that they detect in the cameras, and that gives you a point cloud, which is unstructured. And then, in order to get some simple poses, for example, if they are not very very detailed, you can do it in many ways. One of the ways is that you detect key points in there and estimate the pose, for example. The ones in particular in here were done with some of the paper that we used, MOSH, which simulates some key points on the surface and extracts the pose from there.
Okay, brilliant. Thank you.
Sure.
Thank you very much. We go to our fifth talk. It will be presented by Albert Mosella-Montoro, and it is entitled SkinningNet, two-stream graph convolutional neural network for skinning prediction of synthetic characters.
Hello, my name is Albert, and I will present my work on SkinningNet, presented at CVPR 2022, and developed during my PhD at the UPC. Also, I will present, or I will show you some preliminary results of the new version of this paper that I'm developing right now at Epic Games. Then the goal of this work is that given a mesh and its skeleton, we want a method capable of predicting the skinning weights of a synthetic character. These skinning weights will be used to generate more animations. The requirements of this method is that the method should be independent of the topology of the skeleton, meaning that it should work with humanoids, animals, fantastic creatures, and so on. Also, we want to be independent on the number of vertices and joints. And the method should be permutation invariant. We call it the method SkinningNet, and this is the architecture that we are going to see on detail. The first part of the network are two independent branches, the mesh graph network and the skeleton graph network, that are in charge of process the mesh and the skeleton independently to learn the characteristics of it. After that, we have the mesh skeleton graph network that is the one in charge of learning the relationship between the mesh and the skeleton. And with this information, we are capable of predicting the skinning weights for the mesh. Then, the three branches, where four, are using graph convolutional layers, and in this case, we are using our own graph convolutional layer, the multi-aggregator graph convolution. The motivation for doing this new layer is that most of the previous methods in graphs are not capable of distinguishing neighborhood with identical features but different kernelities. What it means is like, for instance, in this here, we have three neighborhoods that have different features, but all of them leads to the same feature using the aggregation, using as aggregation the average. And on the right, we have the same thing, but using the aggregations as aggregation the max. Then for our case, for our scenario, we want to be able to distinguish these differences in the neighborhood. To do that, we propose the multi-aggregator graph convolution that is just where we just let the network learn how to combine different aggregators to generalize to unseen topologies. Then, in architecture, the first thing that we have to do is to convert the mesh and the skeleton into a graph. And also, we have this sky binding state that I'm going to explain later. Yes. To convert the mesh into a graph, we have two methods that we are using. The first thing is that we are using the one-ring neighborhood that is just converting the faces of the mesh into undirected edges. And the second one is a radius, which consists on using the vertices inside of a radius that we define. Both neighborhoods are used in this architecture, and we are going to see later where we are using that. The second one is the easiest one, how we convert the skeleton into a graph. Is basically we use the bones as edges of the new graph, and these edges are undirected. In the other case, the edges was undirected too. Then the skin binding stage, it takes care of to know which joints are influencing each vertices of that, or which are the candidates to influence each of the vertices. To do that, we propose a new algorithm that is called the K-unique joints of the nearest bones, which consists on computing the distances between all the vertices and all the bones, sort these distances, replace the bones with its root joint, and select the K-unique joints of that. Then the mesh network and the skeleton network shares more or less the same architecture. The main difference resides in the mesh network that uses residual blocks, and well, the idea of that is because the mesh is a more complex structure and we need a more complex network to deal with it. The skeleton usually are more simple and we don't need that much layers to process the skeleton. Then the mesh skeleton network have two major parts. The first one is that with the output of the previous layers, we compute a global shape descriptor from the skeleton and for the mesh. And the mesh skeleton multi-aggregator graph convolution that combines both outputs and learns the relation between the mesh and the skeleton. That outputs a new graph that contains contains nodes with the joint information and the vertices information. Then, for the next stage, that is the skinning network prediction, we are going to use just the information from the vertices. This new network uses a multi-network graph convolution that is just the use of the previous multi-aggregator graph convolution in a multi-neighborhood fashion. Here we use the radius neighborhood that we said before and also the one-ring neighborhood. Then the results, well, we evaluated our method on the RingNet dataset, and as a result, we get a 20% of improvement on the deformation error. Another experiment that we did is the generalization study. This generalization study consists on using the previous network trained on the RingNet dataset that contains simple shapes, simple meshes, used in a more complex scenario with more complex assets. You will see that we have in the left, yes. In the left, we have the neuroskinning results, on the middle, the RingNet, and in the right, our results. And as you can see, our method generalized quite better than the previous state of the art. Then, in summary, in this paper, we presented a two-string graph network that better learns the relationship between the mesh and its associated skeleton, the multi-aggregator graph convolution that better differentiates equivalent neighborhoods with different cardinalities, and using those things, we get a 20% reduction of the deformation error with respect to SOTA, and also we get better personalization capabilities for complex AAA characters. Then, now, what we are working right now is the version 2 of this method that I presented right now, and the idea is that the SkinningNet that I presented before, it supports non-watertight meshes, but the results of non-watertight meshes are not super good, and we are trying to improve that. Also, the problem is that when we are doing the training, we work normally in triangular meshes, but we want our network to be independent of that, it's completely independent, and we want to work in triangular and quad meshes. And finally, we want to be able to handle highly dense skeletons, assets with complex clothing, complex armature, and so on. Then to do that, we have our internal dataset at EPIC. And as you can see here, we have a lot of variability, but not too much assets to use for training. And you will see here that we have assets from 4K vertices up to 16K. Again, for the joints, we have the minimum number of joints are 57, up to 200 joints. Then Some of the qualitative results that I'm going to show, first I'm going to show you some results on Oro asset that if you play Fortnite is one of the characters from Fortnite. You see on the left the ground truth and in the right the prediction. While in the video the predictions, it seems to be super cool, right? We have some errors on the hips, and also in the legs, but yeah. Then if we look at that in more detail, we can observe that there are some deformations on the hips. Also, we can find some outliers also on the hips too, sorry, in the ribs. And finally, we have also issues on the legs and on the, yeah. And another result is oppressor. This works quite better than the other one. You will see that there are some issues on the hips too, in the tabs that we have on the hips. But also we found some issues on the feet. If we look closely, you see here the deformation that we have on the hips right now. And also we have an outlier that in the video cannot be appreciated, but in the shoulder there is some vertex that it's going somewhere, but we don't know why for now. And that's all. Thank you for your attention.
Thank you. Questions? Yes.
Thank you. Thank you for your presentation. It was a very nice presentation. I have just two questions. First, you didn't mention that while creating a skeleton, have you selected a fixed number of joints?
So can you repeat?
When you create a skeleton for a human or any object, did you fix a number of joints that has, or how you differentiate between the joints?
I mean, I don't differentiate any. I mean, I'm using different number of joints and vertices, and my network supports different joints of vertices. That's it. I mean.
So how you differentiate?
I mean, I'm using sparse tensors to do that. I can't differentiate it because at the end of the day, what you do is compute the loss for each of the samples, right? When you do a batch in PyTorch, you normally assume that everything has the same size, but you can apply the same thing when you don't have the same size. You just use sparse tensors to do the computation, and that's it. But it's the same idea behind.
Okay, thank you.
You're welcome.
Any other questions? Yeah, please.
It's not a question, it's like out of my curiosity. So if we have multiple objects inside the scene itself as a part of the skin, for example.
And I mean, if I understood correctly, you mentioned that in one scene might be more than one object, right?
Yeah.
No, that is not the case, because in here what we want to do is we have a mesh and a skeleton that is done for an artist, and we want to predict the skinning weight. We are always going to have just one mesh and one skeleton. We are not going to have multiple objects. It's not part. It's out of the scope of this project, and it doesn't make any sense, right? Because the skinning weights are used during the artist process when they are creating the mesh, doing the animation, and so on. And they normally do that one by one. They don't animate all the characters at the same time. Doesn't make sense.
Thank you.
You're welcome.
Thanks for the talk. One question. Did you have to enforce with architecture that you're using or with the method itself locality of the skinning weights that you get, or could you learn that directly from data? Because that's typically one of the problems in nice assets. You want local weights. If you learn everything, maybe if you have tons of data, you can learn it, but I haven't seen that yet.
No, me neither. I mean, to answer your question, in the first part of the network, in the SkinningNet that we presented in CVPR, we didn't do that, but in the second part, yes, we did. We
you
use the
did
Laplacian.
enforce it with the architecture locality, or?
I mean, we are forcing in the laws for now.
Okay. Well, but okay. If you only do it with the laws, so the network potentially could generate networks that are non-smooth, non-local, but with the laws you can achieve that. Oh,
for now, yes, we are doing that. Yeah.
That's nice. Thanks.
Thank you very much. Thank you. We came to our last talk for this session. This will be presented by Agatha Lapedrisa, and it is entitled Interpreting Phase Inference Models Using Hierarchical Network Dissection.
Okay. Okay. Hello everyone. I'm Agatha, and the work I'll be presenting today on interpreting phase inference models is a joint work with Dibian Teotia and Professor Saros Tadavas from Northeastern University. So basically, the motivation of our work is that we have seen this significant improvement in deep learning-based phase classification models in the past years, but we have seen also these concerning biases and poor performance in underrepresented classes when they are deployed in real settings. So basically, our goal with this work was to add transparency to these models. So, and in particularly, we want to add transparency with explainability techniques that attempt to understand the representations that are learned by these phase classification models. And the second goal is to explore the use of these explainability techniques to reveal biases that are encoded in the model. So, main idea, imagine that you have a convolutional neural network for phase classification, for instance, for apparent age recognition. So then we want to focus in each of the layers. Particularly, we are very interested in the upper layers, those closer to the output. And we want to know to what extent some of the units of these layers are acting as detectors of facial concepts like mouth slightly open, narrow eyes, wearing eyeglasses, action units, and so on. So this work is actually inspired by previous work on explainability for scene-centric classification models. And in particular, it's shown that if you train a convolutional neural network for place categorization, you're going to see that some of the units are acting as object detectors. And also, there's this algorithm called network dissection, which is an algorithmic approach that uses a visual dictionary to automatically pair these units or automatically find what units in your model are acting as concept detectors. And as I was saying, this is based in the broadened dictionary, which is a collection of concepts with corresponding images showing examples of the concepts like colors, textures, materials, objects, and so on. So we wanted to adapt this formulation to the case of phase classification models. And of course, we needed a completely new dictionary, which is a dictionary with facial concepts. So these concepts are not useful for understanding how these phase classification convolutional neural networks work. And second, we also needed a different formulation. So our formulation is based on network dissection, but we needed to change the probabilistic algorithmical approach to pair the units with the concepts as well, because we had some challenges in the phase classification models that we didn't have in the scene categorization models. So basically, we first constructed this phase dictionary. So this phase dictionary is constructed with public data sets, and it contains 12 global concepts and 38 local concepts. So by global concepts, I mean those concepts that are not located in a specific area of the phase. They are just distributed across the whole phase. And the global concepts that we have are apparent age, apparent gender, apparent age, apparent ethnicity, and apparent skin tone. And I want to say that Of course, the data sets that we are using are based, so these labels are based on categorical, on social constructs and some stereotypes, right? We know that, and we acknowledge that actually these global concepts are more fluid, but in this case, we are okay with having labels that represent stereotypical judgments, because at the end, we want to know to what extent these type of judgments are encoded in our model. So in terms of the local concepts, they are structured in a hierarchical manner. So we have first the facial parts, like the eye region, the cheek region, nose, mouth, and chin. And then we have some finer grain concepts within each of these regions, like action units or facial attributes. So here you have some examples of our face dictionary for the global concept upper and age. So here are some examples of images that come from the Celeba dataset. And then for the local concepts, so here you have also some examples, and you'll see that, for example, if you focus on the rosy cheeks, you'll see examples of images showing this facial attribute, and we also computed these segmentation masks that are computed actually automatically, so we use facial landmark detection, and we use these segmentation masks because they are going to be used in the, so we need these segmentation masks because they are going to be used in the unit concept pairing algorithm. So in terms of how we pair, how we discover these units that act as concept detectors in our model, so basically we have 3 stages. The first stage, we pair the units with global concepts. I cannot enter into the details, but I can explain you the high-level idea. So basically, imagine you have your model and you focus in one unit. You have all the images in your dictionary. You can compute a forward pass and just focus on the scores produced by this specific unit. And then you want to know to what extent this unit acts as a concept detector, meaning that it produces the highest scores for images that show the specific concept, and then for the rest of images that are not showing that specific concept, this unit produces lower scores. So that's the intuitive idea. So first, we pair the units with global concepts. Second, we pair the units with facial regions. So we find units that explicitly act as eye detectors, nose detectors, cheek detectors, so they are responding specifically to some of the regions of the face. And the third stage, we pair the units with so those units that have been paired with local concepts in stage 2, then we check if they respond to finer grained concepts in that region of the face. So for example, if you found one unit that seems to be responding to the area of mouth, then in the third stage, we try to see if this unit is responding to a more specific concept within the mouth. So basically, we can, so with this algorithmical approach, we can then produce these types of reports that I'm going to show you. So this would be the report for a ResNet 50 trained for upper and age estimation. So what you see in the x-axis are the different concepts that we have in the dictionary. On the left, we have the global concepts, and then on the right, we have the different local concepts. And then at the bottom, you'll see that we have like a color code for the global concept, right? So green is the color code for the age, red for the gender, and so on. So this is how the report for this upper and age estimation looks like. So you see a lot of green, which makes sense, meaning, oh, and I forgot to tell that we are dissecting the last convolutional layer of the ResNet 50, so the one that is closer to the output. So you find a lot of units already that are acting as detectors of a specific age range, which makes a lot of sense. This is another example, which is also a ResNet 50 model, in this case trained for smile detection, so just a binary task whether one person is smiling or not smiling in the picture. And in this case, so an interesting thing is that you have some units that are acting as detectors of narrow eyes or high cheekbones, which actually seem to be correlated with the action of smiling, right? When you smile, you close a little bit your eyes or your cheeks are raised up. So that makes sense. So one thing that we were surprised about this report is that you see a lot of red. And if you remember, at the bottom, you have the color, this color code, and red corresponds to gender, meaning that there are a lot of units in this last convolutional layer that are actually acting as gender detectors. And this is something we wouldn't expect in a smile classifier. But then we checked the data, and we realized there was a bias in the data. So there were more women smiling than men. So basically, So the model seems to be realizing that learning to recognize apparent gender is useful for the task of smile classification. So this is one of the motivations of the next question that we were exploring, which is can hierarchical network dissections, so this algorithmical approach, reveal biases in the representations learned by the model? And here we performed a collection of controlled experiments. I'm just going to very briefly explain one of them. And this is bias introduced in the local concept eyeglasses. So basically, we have one target task, which is apparent gender recognition. And then we created data sets with different degrees of bias, from balanced to fully biased, associated to the eyeglass concept. So balanced data set would mean that half of the males are wearing eyeglasses in our training data set, and half of the females are wearing eyeglasses on the training data set. So completely balanced in that sense. Then fully biased, all the males in our training data set are wearing glasses, and none of the females are wearing eyeglasses. And then this means that apparent gender recognition will be equivalent to the problem of wearing eyeglasses, which is also a computer vision problem that has a more salient information in a specific region of the face, which would be the eyes. And then we created data sets with different degrees of biases. And for all of them, we trained a ResNet 50 model. And what I'm going to show you here is what happens. So in the x-axis, you have the different facial regions, like eye, chin, nose, cheek, and mouth. And then on the y-axis, you have the count of the units that seem to be responding to each of these regions. And then with the different colors, you'll see the balanced model is going to be in green, and then in red the next one, and then the fully biased in this kind of bluish purple. So this is how the overall report looks like. So what you observe is that in all of the cases, it looks like the model is really focusing on the eye and the cheek region, but you see that as the bias increases, the model is putting more effort in, so the units are putting more effort in the eye region, and they are decreasing the effort on the cheek region, which makes sense because in the eye region is where you have this salient discriminant information of the eyeglasses, which is at the end totally aligned with the target task, which was gender classification. Okay, so I want to discuss very briefly the limitations. So there are many facial concepts that are not included in our dictionary, and of course this limits the interpretability capacity of the model. And also, if we could increase the number of examples per each concept, so probably we will get better results as well. And the second limitation that I want to highlight is that, as I said, the segmentation masks were computed automatically, meaning that there's some degree of noise, which is acceptable enough to have results that are statistically significant. But of course, if we do a manual correction of this segmentation mask, probably the results would be better. And then in summary, so we proposed this formulation, this hierarchical network dissection, for understanding the representations learned by face classification models. We dissected several models, so I just showed two segmentation reports, two dissection reports, but you will find more in the paper. And then also we explored a little bit experimentally this potential of explainability for revealing biases, and again, you will find more experiments in the paper. Here you have the reference and the GitHub rep of our code, so thank you.
Thank you. Thank you very much. Questions? Long way.
Thank you very much for the talk. I have two questions. The first one is that, are you using, I think that you are using a metric between the concept and what the unit has learned in order to decide if this concept is learned by this unit, right?
Yes.
Okay, so my second question is, have you tried to change the metric that you are using to compute the distance? Because maybe a concept that is learned with one metric stops being learned with another metric. So I would expect that if this is a strong concept learned by the net, even though I change the metric, these remain learned. I don't know if I have...
Yeah, thanks. This is a very relevant question. So actually, it's not exactly a metric what we use. So as I was saying, you focus on the unit, and you check the scores the unit produces for all the images that you have in the dictionary, and then you use a statistical probabilistic approach to see to what extent, it is responding more strongly to some concepts than others. There's one significant difference between the global concepts and the local concepts. So for the global concepts, you just use this score. For the local concepts, you also use, as I was saying, the segmentation masks, and also some kind of segmentation that you create in your feature map, right? So it's not about what is the highest score that you have for a unit across the whole, all the locations, but also in a specific location that you know that overlaps with the other location, meaning that if you're going to call it measure, here you are using two things, right, which is the score and also the area. So we already have this distinction, but I think that exploring other ways of measuring or computing, quantifying this, this match, it would be very interesting. Yeah, thank you.
I suggest we continue discussing with a glass of vermouth outside. What do you think? Thank you, everybody.
Aquest el moc d'aquí, aquest el deixo allà?
Sí, per això buscava la Laia, però no la veus?
Crec que... Espera, pregunta-la.
No reconeixia aquest d'això.
Vale, llavors has agafat l'oficial.
Sí, l'oficial està aquí. I l'únic que se li fa és treure-li l'HDMI. Però l'has de provar, perquè jo tinc un Mac i no em funciona. Sí, és que jo he flipat, perquè a més no em funcionava la wifi per connectar-ho. Clar, és el que he fet jo.
Digues que ja.
Hi. ¿A qué no va? Let's start. Let's start with the second session. Welcome to the second session of the Deep Learning Barcelona Symposium. I'm Coloma Ballester. I'm from the Universitat Pompeu Fabra. It's my pleasure to, in this session we have 6 talks, not 7 but 6 interesting talks. And now it's my pleasure to introduce you the first speaker, Xavi Suau from Apple, and who will talk about... go ahead.
No, it's not on me. Okay.
Yeah, go ahead.
Hello? Okay. Hello? Okay. Hola a tothom. Welcome everyone. I will present the work Self-Conditioning Pre-trained Language Models, a joint work with Luca and Nick at Apple that we presented at this year's ICML.
Please. Thank you.
Conditioning language models is expensive. Recent methods rely on fine-tuning or retraining, which becomes prohibitive as the size of these models just increases. Moreover, language models perpetuate bias in the training data, which affects negatively the conditioning and the generation. In this work, we present an efficient conditioning method that leverages already existing mechanisms in the language model. We mitigate bias in our experiments in a large gender bias study, and also we show results on a fine-grained conditioning of these language models. So conditioning a language model can be expressed as maximizing the probability of a sentence X given a concept C. It is very common to tackle this problem by using this factorized distribution where the output probabilities of an unconstrained language model are adjusted through a second model in green. Recent state-of-the-art methods like fudge and PPLM assume the second model external to the unconditional one, or the blue one. In our work, our hypothesis is that the pre-trained language model already behaves in a factorized way, so that both models coexist in the model. So our proposal here is how to find the green model inside the large blue model as a set of expert units or neurons. In order to work with concepts, we first need to characterize a concept. We represent a concept by using a data-driven manner, so by collecting positive sentences and negative sentences, where positive sentences contain the concept and negative sentences do not contain the concept. This is a very flexible representation that allows to represent many, many concepts. And actually, in practice, we only need to collect a few positive sentences, since negative sentences can be just randomly sampled from a large pool. Once we have a concept represented with this binary data set of sentences, we feed all these sentences through the language model, and we collect the response of each neuron in the language model with respect to all these sentences. And then we measure how good each neuron is at classifying the concept. So something similar to what Agatha was presenting in the previous session. In order to measure these precision, we compute average precision, taking the response of each neuron as if it was the prediction score of an already trained binary classifier. This average precision will be what we call expertise for that unit and that concept. Moreover, leveraging the same forward pass, we can also compute the expected value a neuron would output if the concept was present in the input. We do that by simply just considering the positive sentences, and the obtained value will be very important for conditioning later on. So summarizing the algorithm, it's a very simple algorithm in practice. We first identify a set of expert units, so those with the highest average precision in the whole model. And then we intervene upon them at inference time by setting them to their expected positive value. By doing so, we maximize the conditional expert, and the model is able to be conditioned by just poking on these very few units in the model. So for example, for a kind of neutral prompt like once upon a time, if we condition for concept football, the language model might continue with something like a player kicked the ball. So this method doesn't require any retraining or fine-tuning, and it's applicable to any off-the-shelf pre-trained language model. And also it's very simple to implement, since we only compute average precision, and the intervention operation here, the setting the units at inference time, can be implemented with PyTorch forward hooks or TorchFX, so very simple. Now let's dive into the results. The first results are about a gender bias study. We used more than 1,000 prompts that biased the model to a greater or lesser extent. And following Vig et al., we measure the probability of word she or he after the prompt as a measure of bias. So we define bias as the difference in such probabilities. So a model is unbiased if it outputs he or she indistinctively. And we define also the parity point as the level of intervention or the strength of the conditioning that is required to achieve zero bias. In this first result, we show the bias evolution. So in the y-axis, we have the bias, and in the x-axis, we have the strength of the conditioning. So at 0 means zero conditioning, and then more units are intervened as we go to the right on the x-axis. And on the top plot, we see all the prompts that initially have negative bias. So they bias the model towards man as we increase the conditioning for concept woman. And we see that at some point, they all cross the zero horizontal line, meaning that we achieve zero bias for all. On the bottom plot, we see the opposite. So we see all those prompts that initially bias the model towards man, so positive positive bias. And so just that's the way it's defined. And as we increase the concept man, the bias is diminished. And at some point, they also cross the zero horizontal line. So overall, we can achieve zero bias for all prompts by setting or by intervening upon less than 30 units, which is really small compared to the size of GPT-2, which is the model we used here. Now the question is, how good are these sentences at parity? So we can achieve parity, but maybe the sentences do not look good. Maybe they are not understandable, maybe just they are just deterministic, etc. So to address that, we compute perplexity as a proxy of quality and self-blue score as a proxy for diversity. With both metrics, we outperform state-of-the-art by a large margin, according to these results. Another interesting result is the following. So the intuition, if we think about it, the intuition is that if a model is really biased, strongly biased by some concept or some prompt, it should be quite hard to overcome that bias. So we should need strong conditioning, or at least stronger conditioning than for a model that is slightly biased. So we should observe some kind of correlation. And this is exactly what we show here. On the x-axis, we are showing the unconditional bias of the model, so the bias of the model when there's no conditioning. And on the x-axis, on the y-axis, we show the parity point, so the strength of the conditioning required to achieve parity. And we see that our method shows a much stronger correlation. That is really interesting because, one, it tells us that we're capturing bias in the same way that it is captured internally in the model. And secondly, it opens the door to automatic bias mitigation as future work. Some extra results in terms of conditioned text generation. So in here, we're using these prompt that OpenAI made quite famous when releasing GPT-2. It's about scientists in the Andes that discover unicorns that speak English. So a very strange prompt, but kind of useful for this task. And then we intervene upon the 60 top units for concept frustration in this case. So we mapped more than 1,600 concepts, so we can really choose. I'm just going to show you 2 examples. So the first one is for concept frustration, and we intervene upon 60 units. So that's really small compared to the more than 400,000 we analyzed in the model. And that's even smaller than the full size of the GPT-2 model. So by doing so, the model continues the sentence, still talking about scientists and unicorns, but in this case it injects some words or some concepts related to frustration, and I just highlighted them in orange just so that they are easier to spot. So for example, spent a lot of time, did not have success, lone unicorn, remote mountain, etc. The second example is for concept smoke, in the same setting, and now the language model still talks about the researchers, but in this case they had to use fresh inhalations to extract the smoke. So the plausibility of these texts, of course, it has to merge two concepts that are really different, and so it does a pretty good job, but of course sometimes it's just kind of hard even for a human to include that concept. Funnily enough, the study had been approved by the Spanish government, so don't know. So to conclude, we defined expert units as those neurons in the model that self-condition a language model, and I want to remark that those units already exist in the pre-trained model, we just find them. So that's a natural mechanism that the language model has generated while being trained. We just find them and then intervene upon them so that we can condition pre-trained models. We presented the gender bias analysis, quite large scale, where we show that our method achieves lower perplexity and higher diversity in terms of self-blue score than state-of-the-art methods. And also our conditioning is correlated with the model bias, which, as I said before, opens the door to interesting future work. And also we showed some examples on open-ended condition generation. For more details, more examples, and other experiments, please refer to our paper or check out our code from the Apple GitHub. Thank you. Happy to answer any questions.
Thank you very much. Thank you very much. Questions? Mm-hmm.
Hi, I have a question. When you select the experts, do you select them based on any relationship among them? Do you just randomly sample and then pick the ones that are activated? Do you establish any relationship between the experts, or do you just assume them to work individually? Yeah. How do you?
So we assume them to work independently, and we just select them greedily, like sorting them by average precision and starting from the top and then going down until like the top K. They are scattered in the model, so they don't come all of them from the same layer. We have some studies there on which layers capture more concepts, etc. And we saw that like the first third of the model captures more concepts than the later layers. But we don't assume any correlation. So that's also future work, considering some joint distribution of experts instead of just independent experts. Yes.
Okay.
More questions?
Thanks.
Hiya.
You're welcome.
Hi, thank you, nice talk. I was wondering, because if I understood well, with your approach, you go to achieve gender parity, right? With your
Sorry,
data.
can you, because the loudspeakers are pointed towards.
Can you hear me? Yeah?
Yeah, a little bit louder.
So with your approach, you go to achieve gender parity, right?
So with our approach, basically you can condition language model. You can steer the behavior, or you can increase the presence of a concept in the output. And then we showed that one application is studying gender bias and trying to mitigate it. It also basically shed some light on how gender bias is encapsulated in these models and how we could even mitigate it automatically in the end. But so the main goal is not to mitigate gender bias, is to just condition the language model.
Okay.
But one nice application that is actually quite sensitive is addressing gender bias.
So in case you wanted to consider more than 2 genders, like considering non-binary people or non-normative genders, you could do it because it is not just, it doesn't work only for 2 genders.
So,
it is.
In the study, because of the availability of sentences, we focused on this binary and wrong assumption, and we also talk about this about it in the paper. If you wanted to consider like a multi-class, let's say, concept, you could do it one by one, or you could, instead of having a binary representation of the concept, you could have a multi-class representation of the concept and finding those experts that are better multi-class classifiers. But we haven't tried that. But that's interesting.
Okay, thank you.
More questions? Yeah.
Thanks, very nice talk. I was wondering, you mentioned that your method can be applied to different language models. Still, you need to be able to intervene on the language model itself. And I was thinking that maybe an interesting baseline here, if I understand correctly, will be a purely prompting-based method where you have like a verbalizer for your concepts and you feed that as part of the prompt. Have you considered that? I mean, still your method has, as you said, also the possibility of understanding how the model processes this information, but I was wondering if you considered this sort of lighter baseline.
Yeah, definitely. This work, when we actually did this work, prompting was not so mainstream. Like recently, like 1 month ago, I saw a paper on Archive that actually does that. So, and they cite us. They measure they compare with these 2 approaches, like one, the intervention, and the other one, it would be a dedicated soft prompting, trying to identify, or to steer the behavior. So yeah, it's already been done. I forgot the name of the paper, the title. So.
Thank you very much. Maybe we will leave the next questions for the lunchtime. And let's go to our second talk by Ariadna Sànchez from Amazon. Thank you. Thank you, Javier. Ariadna will talk about Unify and Conquer, how phonetic feature representation affects polyglot text-to-speech.
Thank you. Can you hear me okay? Yeah, okay. Ha funcionat abans, però ara...
Sí? Ara?
Vale. Sí? No funciona. Sí, funcionava abans. Sí, sembla com que ho fa, però...
Let's give a speaker, and try to do it afterwards. Pau Rodríguez. We will take advantage of Pau. Pau Rodríguez will be our next speaker, and Ariadna afterwards. Pau will talk about multi-label iterated learning for image classification with label ambiguity. Pau Rodríguez works at Apple.
Sí, abans ha funcionat.
Ha funcionat amb aquest cable?
Sí. Que torni ja aleshores.
No, diu que no. No hi ha, però...
El Mac reacciona quan has fet això?
Sí. De vegades, com que és un sistemàtic àster, que és Windows, no s'entén. Per això sempre diem. No teniu la presentació en un altre format per fer-ho en aquest portàtil?
És que és en Keynote, que és a...
Ja. Sí.
l'HDMI, que no sé una cosa del cable. L'altra opció és enviar-ho per email.
Tampoc va, no?
No. Llavors, no, sembla...
Just in case, the next speakers could send by email their presentation in order to use that laptop, just in case.
Perquè és que si aquest funciona...
Ja, sí. Ara ja és cosa nostra. Hem d'intentar que funcioni això. A veure.
Que no sé quin és el d'aquests que va cap avall.
Ja està.
En teoria... No? Desconnectat.
Sí, aquí sembla que sí que fa alguna cosa.
Sí, alguna cosa.
Cap problema amb el seu catxarro ara?
Sí, la llum d'aquí de les xarxes.
Ah, no?
No sé què fer, és que no sé...
No és que es connecta la xarxa i llavors no arriba allò de la senyal.
Es veu en blau encara. I el cable de xarxa... I ara? Ara baixa la Núria. No sé què més fer.
Perquè si hi ha un meeting obert o alguna cosa, com connecta.
Però és que no arriba la senyal fins a...
No, sí, estava desconnectat.
No, per internet.
Vale, fem una cosa, canviem l'espart. Canviem l'espart.
Canviem espart.
Sí, exacte, directament.
Sí. El que s'haurà...
Vale, espera.
Podem ajudar amb alguna cosa? Coses del directe. Jo pensava, tants canvis, al final... Carlos sí que el detectava, perquè ha fet un...
Però deu ser que allà no arriba la senyal.
No, no m'arriba res blau aquest, sin senyal total. A veure si ara diu alguna cosa.
Està fent alguna cosa. O s'ha apagat.
No, no.
No?
Però és curiós perquè...
Ara no reacciona.
No. Amb aquest com a mínim sí que feia...
Ara ja no reacciona amb cap.
No.
A veure aquí.
Tens pantalla duplicada, no és el rotllo aquest?
Sí, però no... Si et dic, abans ho hem provat tots i ja ens ha funcionat.
A veure si no és l'HDMI o alguna cosa així.
Això no està funcionant.
Una pantalla, sí.
Vale.
Te connecta aquest aquí.
Està el 2.
Vale. Tu no va dir que el trec una pantalla y el posaré.
Es que está el otro, Sparmer, no pilla.
¿Está puesto el 1?
No, está puesto el 1, sí.
Ah, vale, vale. Tío, aquí ahora se queda una pesa.
Pues pitxo el 2.
Sí, sí, lo meto.
Pitxo el otro, tranquila. Ahí para arriba.
Es la presión de clavación.
No lo digas. Pitxo el otro.
Javier, espera, volver.
Es que tanto enchufar y desenchufar el sistema de hecho.
Ya, venga. Ahora está puesto el 1.
Ahora está puesto el 1.
Sí. ¿Qué hago? ¿Pongo el 2 otra vez?
Espérate un momento.
Es que ara ni la pantalla s'encén.
Podeu fer amb un altre ordinador?
Let me just say that we are trying to solve it. In 5 minutes, if it is not solved, we will tell you how to proceed. But we have a certain hope that this could be solved. Yeah. Thank you.
digue'm un email on enviar-ho.
No, a tu mateix i l'home aquí. O algun genèric que us podeu enviar tots. Espera, t'ho tornaré a provar.
It's like the spurious correlation problem. I know many of you have heard about the problem of the cow on the beach, where because all the cows in ImageNet are in a grass background, the model just learns to predict cow whenever there is grass. So the features of the cow are not used. And this is solved by these new data sets like CLIP that have like more detailed descriptions. But for data sets like the ImageNet, this is still a problem. And to solve this, what some people propose, like Lucas Bayer and Olivier Naff, is to relabel the ImageNet. So they just pick a lot of, well, they use actually some powerful pre-trained models, but also people, and they pick every image in the validation set of the ImageNet, and they relabel each image with all the possible labels that it should have. And this is a more detailed description. The problem is that there are bigger data sets than the ImageNet, and doing that, which involves a lot of human effort, is not feasible. And in this work, we try to find a way to alleviate this problem. So we propose MILE, multi-label iterated learning, which is inspired in how languages evolve. So there is this theory of language evolution that it's called iterated learning that says that because transmitting a language from generation to generation has a cost, and it's difficult and it takes time, only those things that are compositional pass from one generation to the other. So languages evolve to become compositional. And here what we try to do is to start from single noisy label annotations and to try to transmit them through generations of teachers to the models in order to build a multi-label representation. And here is the process to train MILE. So we have a teacher model, which we train with sigmoid activations for very few iterations on some single label data. So this is original ImageNet labels. And now we train it for few iterations so that it doesn't overfit the one-hot labels. Now, from this teacher, we span a student model, and we predict labels by doing a threshold on the teacher predictions. Since the teacher hasn't had time to overfit the one-hot labels, it still predicts multi-label predictions. And now the teacher becomes, the student becomes the teacher, and we repeat the process iteratively. So the idea basically is that slowly, because we do this hard threshold on these uncertain predictions, we keep adding labels that were not in the original data set, and then the student learns to predict those labels. And the student is trained with sigmoids again, no softmax. And this is also an interesting thing of this work, which we found, and actually it has been found before, that ImageNet can be trained with softmax and get better performance than, with sigmoid, sorry, and you can get better performance than softmax. And here are some results, and it's fun to see that the original real, this is like the relabeled labels by Olivier and Lucas Bayer, found like uniform and rifle, and if you train with MILE, it finds also the, and even with sigmoid, it finds the pickle hub, which is this helmet that you can see here, which is not super easy to see. And yeah, here you can see the comparison of the labels between, the predictions between MILE, the real re-annotated ImageNet, and the sigmoid. And then we compared the F1 score, so how many, like the intersection with these multi-labels of real, how many intersect. And we find that MILE gets better performance than even sigmoid and softmax. This is top 1 accuracy on the ImageNet. And then, oh, you see my mouse? No. Okay, so in the left is top 1 accuracy on the ImageNet. And in the right, we use Web Vision, which is a data set that is webly supervised, which means that you put in Google doc. You download all the docs, and there's no curation. So it's nice that we found that Mile is also more robust to this label noise. And we hypothesize that it's because of this bottleneck of training for very few iterations that we don't let it overfit on the noise, which requires to use a specific part of the network to memorize that, because the noise is not easy to generalize. And yeah, we presented this at CVPR, but apart from this presentation that I'm giving now, in the paper you can find more results showing that you can use this model to do continual learning, because you can keep adding labels over time. You can do semi-supervised learning and better out-of-distribution generalization. So if you liked it, I recommend you to check it out. And that's it. Thank you.
Thank you very much. Questions? Some questions? Nobody? Ah, yeah. There.
Very cool idea. I was curious about the iterations, like how many iterations do you need? Do you have any idea? Is there like a typical pattern, or is it like typically only having one student already enough to get good results?
We did an ablation on the number of iterations needed for the teacher and the student, so it's a grid. And for a big part of the grid, more or less you get the same results, so that's nice. And the amount of iterations is much less than one epoch. So you do, like, I don't know, 1,000 batches of teacher, and then the teacher becomes a student, and you do 100 batches, and then the student becomes a teacher, and you keep doing that iteratively. Yeah.
And how many, more or less, at the end?
So in the end, it trains for 100 epochs, which is exactly the same as any other model on the ImageNet.
Thank you. More questions? Yep.
Thanks for the talk. Very cool idea. I really like this thing that basically neural networks know more than we are actually asking them, and you're getting that knowledge out. I cannot help thinking or wondering when does it go wrong and how, and if there is any mechanism within this student-teacher that prevents it from going wrong, because I'm sure that eventually it's like the student will get some hard labels that are not the correct ones, and I wonder if those stay forever, or eventually in that process they get removed by some other iteration. What are the limitations? When does it not work?
So you can play with a threshold, for instance, at which you do the hard labels, no? If you put it too low and you make anything above 0.1 to be a label, you will be able to cover more of the predictions, no? But the problem is that you will start to hallucinate also labels. And this is one of the limits, that we set it to 0.5 just because we don't want to enter, like, we wanted to provide a general method, mostly. But yeah, this is, and it's interesting because actually we found that moving the threshold, you can get even better performance. But it has also this double problem. And then there's also the problem of sometimes depending on the hyperparameters. I must say that this teacher-student configuration, it was super solid. Like you could change the number of iterations and it worked well. But maybe if you do too many iterations at the beginning of the student, since the teacher has not yet learned well, it may overfit into something that is not right, basically. So you have to play with these things.
Okay, thanks.
Thank you very much, Pau. And Ariadna, if you want to come back. And by the way, thank you to both of you for adapting to the difficulties. Ariadna Sànchez will talk about unify and conquer, how phonetic feature representation affects polyglot. Go ahead.
Okay, so hope you can hear me okay. So, yeah, so hi all, thanks very much for coming to my talk. Yeah, I'll just be talking about one of the latest papers that we published at Interspeech with my co-authors Alessio, Ziyao, Orazio, and Kayoko. So multilingual multi-speaker models, well, text-to-speech models, which is we call Polyglot in our paper, allows us to synthesize any speaker in any language in the data set. And we can do so right now with high-quality synthesis. The literature shows like two types of designs. So for input linguistic features, we can choose to use what we call a separate representation or a unified representation, which I'll be talking about in a minute. But we saw there was a gap in comparing these two methods and seeing which one would be more beneficial for text-to-speech. And that's basically the purpose of our paper. The paper explores three questions. So the first one is we want to understand whether the input linguistic representations affect the quality of polyglot synthesis in both terms of naturalness and accent in the target language. The target language means is the language that we want to synthesize with, so not necessarily the one that the speaker originally speaks. The second question is whether different representations also affect the quality of synthesis in the target speaker's source language, which that's the original language of the speaker. And the third question is whether there is an impact when we modify phonetic embedding sizes in both representations. Yeah, as I mentioned, we divide the types of linguistic features in two types, separate and unified. A separate representation is what we define as having a separate phone set for each language variant. So basically we have one token per phoneme. And we can see here in the examples, so for each language variant, so like American English, Australian English, etc., we would have a separate token. For a unified representation is what we define as having a unified representation for all these language variants. So as long as this phoneme exists in the language, it will be defined and denoted by the same token. We are currently using XAMPA, which is a machine-readable notation of the International Phonetic Alphabet. Our polyglot text-to-speech architecture is a neural acoustic model that is shown here that converts phonetic sequences into MEL spectrograms, and then this is followed by a universal neural vocoder. And for, well, basically, the neural acoustic model is composed by an encoder, a decoder, and an attention module. And we also have a flow variational autoencoder to model the speaking style of the speaker. And then to make this model multi-speaker and multilingual, we also have external conditioning in the form of a speaker ID, a language variant ID, and a language ID. This would be the neural acoustic model for the unified, for the separate representation. But I have to note here that for the unified representation model, we drop language conditioning, so language ID would not be used because it causes accent leakage. And we've seen that this is basically adding redundant or confusing information can be detrimental for our models. So the data composition of the models, it's basically the same for both. We just changed the input linguistic features. We use 130 speakers from 12 language variants, which across 4 languages, as we can see in the table here. For each speaker, we use 3 to 6 hours of recordings, except for the target speaker, which is an American English speaker, where we use 30 hours of recordings. To evaluate the model, so we train one for each type of input linguistic feature, and we evaluate them in 4 language variants, so it's German, French Canadian, British English, and American Spanish. We also want to evaluate the quality of the synthesis in the source language variant, which, as I mentioned, is American English. And we do all of this with using a Mashra test, and we do separately Mashra tests for naturalness and accent, and we test on 100 utterances. So before I dive into the results and I show the Mashra results, I also want to explain a little bit the x-axis, so the different systems that we use. The system name called recordings, it's what we use as an upper anchor. And for naturalness, it's the target speaker recording, so it's the American English speaker, its original recordings. And for accent, we would be using as upper anchor the recordings of a native speaker in the target language variant. So for example, for the German evaluation, we'll be using a native speaker of German. Then separate and unified corresponds to the models that we've trained with the different features. And monolingual, we're only using this as a lower anchor for the accent evaluation. And here, this would be the synthesis from a model that has been trained with monolingual data of the target speaker. We use phonemes of, like, for example, let's say German, but we map them to what a monolingual speaker of English can do. So we basically map German phonemes to the most equivalent phonemes for American English, and therefore this results in a heavily accented English speech, and that is why we use it as a lower anchor. Yeah, so here we can see the results of the Mashra tests. We can see the ones for naturalness and accent for each different language variant that we evaluated. Overall, we see that the results for the unified features are statistically significantly better across all locales and naturalness and accent compared to the separate representation. And also one thing that we saw during informal listening is that the unified representation models are actually more stable, and they're like less prone to have errors like mumbling and skipped punctuation, which is something that we see quite often with attention-based models. As I mentioned, we also checked the source language because we wanted to see whether the polyglot models had a degradation in the source language compared to a monolingual monospeaker model. So as we can see here in the Mashra results, they're quite similar across all the different systems. So that means, and the results are not statistically significant, so that means that all models produce a very similar output, a very similar quality for the language, so there is no degradation of the polyglot models compared to the monolingual model. We also wanted to compare the speaker similarities, so to see whether we had any sort of speaker leakage in the model. And for that, we use an open source package called Resemblizer to calculate speaker embeddings. And we compare them against speaker embeddings from the original speaker, from the recordings. And as we can see here, we calculated cosine similarity. Yeah, we can observe that the monolingual model is still the closest one in terms of similarity to the recording, the embeddings of the recordings. But the unified features are better than the separate representation. So it sort of bridges the gap between the two types. Finally, as I mentioned, the third question was whether changing the size of the phoneme embedding vector would affect quality of synthesis. So for this, we trained polyglot models with the two types of features, but using different phoneme embedding vector sizes, so 64, 128, and 256. The 256 value is what corresponds to all the previous models that I've been talking about. So we just sort of made the embedding size smaller. So yeah, just to briefly talk about all of these results. Comparing separate and unified for different embedding sizes, we can see that for the unified representation, a higher embedding size is preferred. So the 256 is preferred across all locales and for both naturalness and accent. But for the separate representation, there is no clear correlation that a higher embedding size is better. We also wanted to compare, like, for the lower embedding sizes, whether a separate or a unified representation would be better. In this case, also, we can see there's no correlation or no preference. So as we've seen before, for the 256, there is a preference for the unified representation. But in this case, yeah, so for lower embedding sizes, there's definitely no preference. Yeah, so just to summarize the key takeaways, the unified representations are statistically significantly better than separate across all the language variants for naturalness and accent. We also observed that these models, the unified representation models, are more stable. We also have shown that polyglot text-to-speech synthesis doesn't show degradation in quality against a monolingual monospeaker model for the source language variant. We've also shown that unified representation scores better speaker similarity than separate, so it brings it closer to the performance of these monolingual models. And for the ablation study, we've seen that for unified features, bigger phoneme embedding sizes are preferred, and there is no significant difference for separate features. And finally, also that the differences between the unified and separate features are not statistically significant at lower embedding sizes, only at higher ones. And just wanted to briefly mention that we've got another paper in polyglot text-to-speech that was published at Interspeech. I don't really have time to talk about it, but we just do a very dive deep in data composition for polyglot models and just try to show best practices when training these models. So yeah, so if you want to check out, feel free to do so. And yeah, that's everything for me. Thank you.
Thank you. Questions? Let me start. You said that the unified representation allow bigger sizes of the phoneme embeddings, right? Mm-hmm. And have you thought of applying this to remove redundant tokens? Or redundancy in general?
Right, so yeah, so the idea of the unified representation is actually to remove these redundant tokens, right? Because we've got so many tokens that could be shared across language variants. So that is definitely the whole purpose of the approach, yeah.
Yeah, thank you.
Yeah.
More questions? First, let's thank to Ariadna again. Next talk is by Adrià Recasens from DeepMind. The title of his talk is Game Plan, What AI Can Do for Football and What Football Can Do for AI. The floor is yours.
Thank you so much for the introduction. Yeah, I know you haven't heard about football for the last 3 weeks, so I thought it was a good moment to present our work on football analytics. So this is work from many people in DeepMind. You will see them listed in the slides, and it's actually a collaboration with Liverpool Football Club as well. So to motivate this work a bit, I just wanted to show you a little clip, and then we'll talk about it. So in this clip, you've seen a goal that it was scored like a few years ago by Aleix Vidal. And basically, this is the way we always consume soccer, right? Through the broadcast that we see in TV, where basically the camera kind of goes through the different parts of the action and essentially shows us everything. However, if you look at basically the state of the art in sports analytics, you will see that video is not as used as other modalities that are essentially compressed information of what you're seeing here. So one of these modalities is event sequence, where basically you can see listed here all the on-ball actions that you saw in the previous video. So essentially, there is one pass from Busquets to Messi, and then another pass to Busquets, and so on. So I think this is a good example of essentially imperfect modalities. So in video, we have a lot of information about what happened, but we don't have all of it. If you remember the goal, actually, there is someone running from behind that we don't see through the game, but it actually through the play. But at the end, it's the one who scores the goal. And in the right one, we have information about who touched the ball at each moment, but we don't have all the context, right? In the video, we see all the players kind of moving around, but in events, we don't. So essentially, football analytics basically is a field where we have a lot of modalities, but they are always incomplete. So we have more modalities. So we have penalty kicks data, where basically we are told where the penalty kick is shot and who shot it. We have tracking data, where basically we know the position of all the players in the pitch, kind of moving around. The issue is that this is very hard data to get, because it requires either kind of a tactical camera that records everyone, or someone in the kind of in the players itself to track them through the pitch. We have also event stream and footage. So essentially, this is something that coming from the coming from the machine learning perspective, it's amazing, right? We have many modalities, we can learn through all of them, and essentially they all together kind of form a kind of better information piece than just using them separately. So I think this is the realization when we published this work last year. So this is a paper that appeared in the Journal of Artificial Intelligence, and as you see here, it's work from many people. And essentially, it's a bit of paper of intentions. We're just telling in the paper, oops, yeah, I need to. We're just telling essentially the story of what we think is the future of football analytics. So I'm just going to go a bit briefly through this paper, and then I'm going to kind of deepen a bit more into a second one that we published this year. So the main story is that machine learning can help. We are in a setting where we have many modalities. We have a lot of tools already developed in the machine learning community to do that. So let's just do it, I guess. And then a few research questions that we kind of pose in the paper are, which aspects of football can be improved? Maybe not all of them, but certainly some of them can be improved by just having a lot of video data, a lot of events data, and using all this together. How much information can be extracted from video? So I think video is underused in the community because it's very expensive to use. It requires some specific abilities from our models. But at the same time, there is a lot of footage from football. So if we find a way of using this, then it's amazing. We can use it for many things. And finally, we introduced this notion of the automated video assistant coach. And I want to put an emphasis on assistant, because it's not that just a coach that it's automatic, it's just helping someone else to actually coach a team. So this was introduced in the paper in 2021. And, okay. And we also talk a bit about the different layers that we think you should go through, so kind of research challenges. One of them is extracting raw information. So again, the example of broadcast is good because we have broadcast, but then from that we can extract signals that are useful. We can do also predictive modeling, so where the players are, who's going to score, and so on. And finally, there are kind of higher level, maybe psychological human factors. We haven't touched on this, but we think it's important to kind of do the full modeling of the problem. So some areas of interest, I'm going to talk about two of them, but just for you to have kind of a broad sense. There is some work on kind of classifying players into clusters. So different players belong to different clusters, and then you can use it to decide. So I guess you can decide doing some who to buy or who to sell, or which players to change, and so on. Also, game theoretical analysis of penalty kicks, trajectory prediction, or pitch control, which I'm going to talk a bit at the end. So let's just start with the penalties. Probably some of you have seen a lot of penalty kicks lately, so I thought that this was a good moment to plug this here. So there has been a lot of work for many years on analyzing penalty kicks, and essentially this work comes mostly from the game theory, the game theory research area. And what they do is they kind of model a penalty kick as a game, where you can kind of kick to the right, kick to the left, and then the goalie can jump to the right, jump to the left, and then there are kind of more actions that you can do, but essentially that's the idea. And what we did is we took this very nice work from Palacios in 2003, and then we kind of added more data, and we also added player context, which I'm going to go in for a minute. So essentially, this work does very nice work trying to put together all these different statistics on how players shoot penalties, but they don't take into account that maybe some different groups of players shoot differently, right? I mean, they can be left-footed and right-footed, and this is very obvious, but there could be a lot of different properties that make them kind of do things differently. So instead of having one aggregated model for all of them, what we did is we clustered the players using player vectors. So this is not our work. Player vectors is a paper from 2019, and you can see how you have these kind of different clusters of players. And then what we do is, for each of the clusters, we analyze how they shoot penalties. And what you find is that depending on the clusters, some of them shoot the penalties more into the right, some of them shoot the penalties more into the right, the left, and so on. So I guess the general insights, because I'm a bit short on time, is that either if the player is left-footed or right-footed, it actually doesn't matter much. What they call the game behind that is essentially the same. It seems to exist a bit of a mind game, which I guess it was expected, between the goalie and the striker that is kicking the penalty. So depending on what one does, the other does a different thing. And finally, there is this notion of the players playing an epsilon Nash, which means they are close to the optimal thing to do, but still it can be exploitable, which is good news, I guess, for people working on this area. And the second part of this talk is going to be about prediction modeling. And yeah, to motivate this, I have another video. So this is a paper that appeared this year in Scientific Reports. And essentially, and I don't know if I have my mouse here. Yeah. So yeah, I thought it was a good day to play a video from Messi. And this is, so this is a penalty a few years ago where instead of actually kicking the penalty directly to the goal, what Messi does is he does a pass. Now, if we freeze the video here, what we find is that we have no idea what's going on. I mean, he has passed the ball, but the broadcast only shows us these two players. And essentially, we know that there is someone coming, otherwise Messi wouldn't do that, but we don't have them into the pitch. So I'm just going to continue the video, and now Suarez comes and actually scores the goal. But essentially, the main story here is that we should be able to fill this gap, right? I mean, we knew someone was coming. Of course, we didn't know who, but there is a gap to be kind of filled in the modality of video. So that's what we try to do in the second paper. What we try to do is to kind of do time imputation to take essentially the observed players from broadcast and add kind of the position of all the players in the pitch, not only the observed one, but also the unobserved one. So I changed the title a bit. I think this is a better title, actually. Football is not what you see in TV. So yeah, the main question is, can we predict the position of off-screen players? And things that you could do with that. One of them is, of course, you can understand better the behavior of players because you could kind of roll forward your model multiple times, and then you have essentially different trajectories of what could happen. And finally, you could also play the counterfactual game, which is this idea of the what if now this player is in this position, or what if this player had done this instead of that, which, of course, for tactical recommendation, it's very, very important. So the problem is we have 22 agents, which are 22 players, and the ball, which is counted as an additional agent, so 23 agents. And what we have is a sequence where some of the agents, we have some observed times at some point, and some of them we don't see them because they are essentially out of the screen. So what we did is we took tracking data, which is basically the data for the 22 plus the ball, and we simulated this camera, which is what you see here. And then essentially we're only taking the data that the camera sees, and we are just now dropping the data that the camera doesn't see. So in a way, we have all the data, and we're simulating a broadcast in order to train our model to predict where the others are. The thing is, we know where the other players are because we have all the data. So now we can train the model to do that for us. So the idea is we have a forward model and a backward model. So the model is not causal. We take the full sequence, we go backward, forward, and then we kind of accumulate the final prediction. And essentially, how the model works is we have observe and predict as entities. We have essentially an LSTM that computes a state that kind of goes time step by time step. And then every state is fed into the graph encoder, which is basically variational. So we sample from this graph encoder, and then we decode it to the final change in position. So we're not predicting actually the position in the pitch, but we're just predicting, like, okay, how are you moving through the pitch? So this is another view of the same idea. We have the LSTM. So we have the encoder that is only used for training, because in inference, we're just sampling the prior. And then we have the decoder, and at the end, we we just predict. And then the right side is the same, but I didn't have space, so we just added this later. So in terms of numbers, one thing that I think it's relevant here is that if you actually look at the prior work, they are mostly football-specific models. They do model how the different players move and whether someone is a striker or not, and so on. And in our model, we're not doing football-specific. It's a model that could be applied, it's applied to football, but it could be applied to something else, basically. And yeah, if you compare to kind of the competition, we get an error of 0.15, which is way below the error of the other models. So yeah, this is very hard to read, but I think these graphs are cool, and you can see basically the error made. This is kind of the main competitor, and this is our model. But as this is hard to read, I have another way of visualizing this, which is overlaying this into the broadcast. So basically here is the predicted position of the players. These are observed, so it's fine. And then the trajectories that our model thinks they have followed, and the trajectories that they have really followed. So yeah, we can play this for a bit, but actually there is, I think, a better way of visualizing this, because the issue here is that we only see the players that are in the broadcast. In here, what we do is we put the broadcast kind of with the full pitch. So now what we can do is we can see all the players, or our predicted players, basically, ground truth and predicted, and then essentially we can see how the broadcast moves backward and forward. So the idea here is that this can be used for many applications, as I said before. So we're using one in our paper, which we think is useful. I don't have time to go into details, but we do what it's called pitch control. And the idea in pitch control is that in a certain situation in the game, there is certain areas of the pitch that one team has the ability of recover the ball. So if the ball now falls, for instance, here, the red team will kind of easily recover it, and while if it falls into the blue area, the blue team will recover it. And then in the kind of more uncertain areas, it's unclear. And there is a lot of work with kind of tactics modeling this, because if you have the right pitch control in the right areas of the pitch, then you can kind of make use of this. So yeah, it's hard to see, but the numbers are in the paper, that actually our model has less error compared to the kind of pitch control compute with the 22 ground truth positions, which is basically what we want, right? Because if we can compute pitch control from broadcast, that means we can extend this work not only to the data where we have tracking, but to kind of all the data that we have with broadcast. So just as a summary, we propose this general framework for multi-agent time series imputation, which we apply to soccer. The graph inputter uses variational graph neural networks to actually predict the position. So we also talk a bit about penalties and how game theory can meet machine learning to improve kind of penalty estimation. And finally, we think that this is one piece of what could be a lot of work on how AI and machine learning can help sports analytics, but at the same time, all of you as AI researchers can benefit from sports analytics, because I think it's an amazing play bet for all our techniques, because it's kind of controlled, it's a nice domain, and we have a lot of data. And also people like it in general, so that's nice. So thank you so much for your attention.
Thank you. Questions? Yep.
Hey, super nice talk, Adrià. I have a question. So all this data at the end is ultimately like consumed by coaches.
Can you talk a bit?
Hola? Oh, yeah. Vale. So this data or the models you have, after you do some value attribution, like I think that this is ultimately consumed by coaches. So how do you explain them? All the, like what your model is doing? Do you have any interpretability like tools or tactics that you can share?
So I think it's an ongoing area of research in general, because there is a gap, of course. One thing is like, okay, the probability of this happening, and then it's the coaches, but it's also the players, right? I mean, there is kind of a chain of people. But I think kind of moving towards visualizations, maybe this is something that coaches in general can understand in terms of, okay, if the ball is here, your team is going to control it. If the ball is here, the other team is going to control it. So I think the community itself has already started working into tools to visualize this, but I agree, a lot of work is needed, especially when we move to maybe more complex models, which are maybe going to do more things, and then it's a bit trickier. Even, I mean, I've been looking at these maps for a bit of time, and I think this is very complex to understand. I mean, there is a lot of things moving here, and of course, when you overlay it with the broadcast, then things get clearer because you see the players moving. So maybe moving towards using more video into the visualizations is also probably a very good idea.
Thanks.
Thank you.
Another question there? Yeah.
Hi, thanks for the talk. The question, I think you said the model you trained is non-causal. Can you comment on whether that would affect whether you could produce overlays in real time for broadcast TV, or is this an issue?
Yeah, so that's a very, I thought I had said this. So the model is non-causal because you run them in the kind of two directions, but actually I don't think anything prevents you to only running in one direction. So you could run it only forwards, and you could keep generating. It would be lower quality, of course, because you're missing the fact that you've seen all the broadcast. But yeah, there is nothing that prevents you from doing that. So I think it's one of the nice properties of the model is that, yeah, the best one is, of course, non-causal, but you could make it causal for practical reasons, and it's fine.
Okay, thanks.
Thank you. A very quick question. For semantics, you only use the fact that there are 22 players and one ball, but not the fact that they belong to different teams.
Yeah, I think that's a good question. I think the way the players are inputted into the model, there is certain ordering, and I think the order matters. So yeah, the model knows who's player, and I think even the order, for instance, the goalies are probably the first one. So this is something that the model can use.
Thank you. Thank you. Let's thank the speaker again. Our fifth speaker is Miriam Belver. Miriam works at Amazon. The title of her talk is Human Body Measurement Estimation with Adversarial Augmentation.
Okay. Hi, so I'm Miriam, and I'm going to present this work about human body measurement estimation with adversarial augmentation. So this is a work that has been done in the fashion team at Amazon, and the first author is Nathaniel, who was interning at that time in the team. So basically here the motivation is to estimate body measurements from silhouette images. And first of all, why do we want to estimate body measurements? Basically, this can be used to tailor clothes for customers, or also for medical or fitness applications. And why do we want to do this from silhouettes? So here the main motivation is that instead of using an RGB image like the one that you can see here that could cause friction in customers because maybe they don't want to share such pictures, we directly work with silhouettes which they are not identifiable. So here the idea is that once the customer takes a picture, we directly get the silhouette, so we only work with those. And then we input this into a body measurement network that is the one that will predict different body measurements. And these body measurements can be girths, like in the waist, hip, etc., or lengths, like arm length. And also it's important here that we are also using height and weight in order to properly scale the measurements. So in order to train such a model, we need a data set. So basically, we collected this data set that we are open sourcing, that we call it Body M. And it basically was first collected using RGB photos, but what we are actually sharing is the silhouettes, as I was commenting before. So these photos are taken in a very controlled setup, so very well lit indoors, and the people were asked to be standing in an A pose. And what we are using for this set of experiments is that these images were collected using tight clothes, so that it's possible actually to be able to measure the different measurements from the body. And in total, we have around 9,000 silhouettes from almost 3,000 subjects. And here what we have two different test sets. The first one that we call test A, it's basically in this super control setup that I was commenting you, but then we have another test set that is the test B, that basically it consists of images that are not that controlled, so they try to pretend like if the customer is at home taking those pictures, so the camera is not that good, the illumination as well, etc. So this dataset, it's public right now, so it can be used, and it's at this date, it's the largest dataset with measurements coming from real images. And here you can see some of the statistics of the different measurements and the statistics from female and male. So here are some more statistics about this dataset that I was commenting in terms of the body mass index. And here what we want to highlight is that so this dataset basically was collected in the US, and we saw that the data that we had collected didn't represent all the populations in terms of body mass index in the same way. So basically some of these groups were underrepresented. So here it's where this work started, and it's basically if it was possible to synthesize these body shapes that we don't have right now in the data set and include them in our training loop so that we have a better representation and that we can, that our network works better for all kinds of bodies. So in order to do that, the idea here is to, as I was commenting, to synthesize bodies using a differentiable body simulator so that we could integrate this into our training loop and basically have it differentiable end-to-end. And what we use is the simple model, which basically is a model for bodies that consists of these shape parameters and pose parameters. In our case, the pose is fixed, so we are using an A pose. So here we play basically with these beta parameters that define the shape in simple. And once we have this mesh of a body model, we are using a differentiable render, so this soft rasterizer that projects and gets this silhouette. So this is the input that then we will use to this second network that will predict the measurements. So also we need to get the measurements, right? So that's what we want to predict with our network. So basically we have this module that from the body mesh, it predicts, like it computes basically the measurements so that we can get this ground truth. And this, basically these measurements are distances between vertices of the body mesh. And finally, as I was commenting before, in order to properly scale the measurements, we need some idea of the height, basically, of the customer, and we are also using the weight. And what we did is from these simple parameters to have a regressor in order to get those. So here you can see the pipeline end-to-end. So first we have these beta parameters that define the body shape. We input those into the differentiable simulator so that we can get these body silhouettes with the height and weight that are coming from this regressor I was commenting before. And then this can be inputs to our measurement estimation network. And that's exactly what you can see here. And then we have the ground truth measurements so that we can compare the predicted measurements with the ground truth. And here what we would like is to know which beta parameters are the ones that lead to a higher loss in our network so that we can find hard examples that in our training loop and in order to improve in those cases. So basically we do that using gradient ascent. And some important detail here is that first, of course, we need to initialize these beta parameters in some way, and we saw that it was important to initialize them using real betas that we already had from our real data set in order to avoid having unrealistic body shapes. So here you can see the training scheme. So first of all, what we did is to take this, this network, this body estimation network is, by the way, it's basically a convolutional neural network that gets us input these silhouettes with the height and weight information, also doing like a dense map of those and concatenating them to the image. And here, so as I was commenting, first we train it with the real images that we have, and then what we did is to simulate these bodies using the simulator, basically, and then add them into our training loop. So at the end, we are fine-tuning using this real and synthetic data. And what we saw at the end, that it's not included here, but at the end we also did a round of training only using the real data at the end, like a small fine-tuning, because we saw it was important to avoid this synthetic gap, basically. So here you can see some of the silhouettes that we are getting with the network, some of the low error cases and the high error cases. And you can see that the high error cases are basically those cases that don't appear that much in the data set, as I was commenting before. So these are cases of a high BMI. And so those are the ones that we would like to improve, right? So because they are not that well represented in our data set, so we would like that our simulator synthesizes this kind of bodies. And here you can see what happens with our simulator in this training loop. So basically when it trains, we can do a baseline that is basically using random betas, so that we are not looking for hard examples, and this is the first row that you can see. And we can do also what we are more interested is like trying to find adversarial examples, which is the second row. And we can see here that the VMIs are higher, so it corresponds to what we were already expecting, because in our case, we knew which was the gap in our data set, that basically we were missing these high VMI examples. But you can see that this method could also be used in other kinds of gaps of data that we may have in our data set. Okay, so here what I'm showing is basically what are, like, in terms of weight and height, which directly correlates to the body mass index, the ones, so what is that this network is sampling when we are using the hard sampling body, so the adversarial one, or the random. And we see that when we are doing the adversarial, which is the first graph, basically there are more samples in this space of a high weight and height. And you can see also the color code, so the darker it means the higher error. So we are exactly doing that. We are sampling more examples with more error, that is what we are intending. So now some results. Yeah, first of all, I think something that I didn't comment, we are not only using the frontal silhouette of the body, but also the side view, which is quite important for some of the body measurements. So that's why here we have this multi-view. So basically we have these two inputs in our data set. And here I'm showing the measurement error in millimeters in terms of percentile, are also the mean average error for some of the most relevant measurements that you can see here. And basically, the first row, it would be without augmentation, only using real data. But then if we do some random augmentation, so basically not considering what are hard examples, we're improving a little bit. But when we are doing the adversarial one, we are improving more. So I think it's important also to know that even with random, you can improve, which is something that it makes sense, right? It's that augmentation. But if you are choosing wisely which data to add, you can improve a little bit more. So here, then we did some other experiments using other data sets. So the first data set, it's a data set with synthetic humans. So in this space, there are other existing data sets that they don't come from real images as the one that, that we are presenting in this work, such as this one that it's basically on synthetic examples. And here we saw that our method also improves the previous model. And then there's another data set that is the second table, that it's this body fit, that it's a more recent work that for training they use synthesized bodies, let's say, but for testing they have a small set of real data. So that's also what we used to test here. And yeah, we saw that our work also improved. And here I also wanted to highlight that basically if you check the difference between the test performance when using real or synthetic bodies, the performance is quite different. So with real, the error is higher. So that's another reason why we think it's important to work with data sets that come from real examples. And that's why we also outsourcing this data set. And finally, here we are doing a final comparison using these models, state-of-the-art models, that what they aim to do is to do human mesh reconstruction. Basically, these models, what they do is to predict the body mesh, and from the body mesh, then we can compute the measurements. Instead of doing direct regression as we are doing, so we are directly predicting, like, let's say, the value of these measurements. And for this experiment, we just used a single view. We didn't use any metadata, so actually there's not that much of a notion of a scale. And we see that we did all this in order to be able to compare to the other methods, but our method still works better. So as a summary, here we are presenting this differentiable simulator that it can automatically discover adversarial body shapes. And we see that it can fill these data gaps and it can achieve state-of-the-art performance. We think that this is very important because now I showed very clearly which was the gap in our data set, but there might be other gaps that we could also cover with such a strategy. And also in this space of body estimation, it promises a more inclusive body estimation, which is very important and also for the experience of the users. And finally, this data set is released. Also, the code of this approach is public. And in the future work, we would like to add basically more dimensions to this simulator. So for instance, for the segmentations that we are rendering, like we are not adding any noise, so you can imagine that they are too good compared to the ones coming from a real data set, and so we think that there's a lot of room of improvement in this space. And yeah, that's it. Thanks.
Questions? I have one. Would you think that it would be useful or interesting for the estimation of some measures, for instance, height, to add an extra augmentation, for instance, removing one leg or something like this, because your frontal views are very, very similar, symmetric, sorry. Would it be useful, or is a silly question, removing?
No, I mean, I think that everything that we can do in terms of that augmentation helps, and also it's true that right now we are only using this A pose, which is a quite convenient one because you can see a lot of details between the legs, etc. But yeah, what we would like to do is also to be able to work with more poses, etc. And I think that anything related with having more diversity in the data set, it would be good, but we also found that this makes things very much complicated. So basically having a constraint in pose helps to get better performance and also to have this very controlled setup. And I think that's something good of our data set, but it's also true that it constrains a lot the possible application, right? Because we are asking to be in a very controlled position.
To be more robust, yeah. Nice, makes sense. Thank you. No more questions. Let's thank the speaker again and go to our last talk. Just our last talk is Xavi Giró, but one comment first. Laia told me the comment. For the poster presenters, if somebody is interested, you can go outside and put the poster on the wall. Our next speaker is Xavi Giró from Amazon. Well, from Amazon, from the UPC, from IRIS also, from CVC. Doesn't work, Xavi? The title of his talk is Towards Sign Language Translation and Productions. The floor is yours.
Okay, so thanks a lot. My name is Xavi Giró. I'm in Amazon Science, but I will basically talk about my work at UPC and IRI and BSc. So I will basically describe the work of Ramoneda Duarte and Laia Torres in the framework of their PhD. So we've been working on sign language translation, especially since 2016. So here's the outline of today's talk. First, I'll try to motivate. Our goal is to empower more than 6.5 million people who are using sign languages. So these are people who have severe or completing hearing loss and that use sign languages, different sign languages, as their main means of communication. So mostly nowadays our technology is not ready to support that, and enabling them with that, that would improve their access to big services like education or health. Not only this, but also like the new devices that we are all building, like Alexa or Google Assistant or whatever, they are mostly making great advances in spoken languages, but not as much on visual languages. So we are exploring this venue. Before describing the techniques that we have developed, I will give you a super short course on sign languages. The first idea to keep in mind is that there's not one universal sign language, and similarly as spoken languages, there are multiple sign languages. So each community has developed their own sign languages through years. So for example, our work focuses a lot on American sign languages, but there could be like the British, the German, Chinese, Irish, Catalan, you name it. The second important idea here to mention is that it is not that one spoken word, even if you have transcription, has a direct mapping on a sign. That's much more complex than this, right? So maybe there's not a one-to-one mapping. So solving sign language understanding for machines is not like having a dictionary and just solving a lookup table. That's much more complicated. Another concept that I will be mentioning today in the talk is this word named glosses. Okay, let me see if I can turn the pointer on. Glosses, okay? So glosses are textual transcriptions of sign languages, right? So if I mention gloss, it would be like words, but words that you use to describe sign language. And the final idea that you must keep into account is that sign language, while most of the information is conveyed on the hands of the signers, that's not the only source of information. There are many non-manual features, basically around the facial expression, but also the body pose, the orientation, that also accounts for fully understanding sign language. So crash course on sign language is over, so now we can start explaining what we have been working on. So the state of the art on sign language, as in any other technique, has greatly changed since the advancement on deep learning, but there are some tasks that I will be looking at today. So probably the most famous task that you can think about is what's called sign language translation, which means that coming from some type of visual features, and in our work, sometimes we directly work with RGB-based features, basically I3D convolutions, if you know what they are, but they are spatial temporal convolutions. But also what you can do is you can extract poses, whether just with 2D coordinates or with 3D coordinates, and that somehow expresses the pose of the signer. So if we start from the pose of the signer, what you can do, we can do translation, but we could also do production. Production would be the opposite way. So there's translation and production. That's why this talk is named towards open sign language translation and production. And there are other tasks like topic detection and sign language recognition that are also in the field. So when if you look at papers about sign language, it's not there's only one task, there are multiple there. And the first thing you need to figure out is which one you want to address. If we want to solve sign language translation, and I'm sure that many of you are from the language community, one basic approach is in the neural field is, okay, I'll try to somehow encode the video, and I'll have my neural representation, and then I'll decode it, and I'll have my translation. Easy, right? And that's what nowadays the state of the art for the last years has been, for example, with this work. You could also do the opposite. If we want to do this to produce poses, or maybe with these poses you want to later condition to generate the RGB frames, you can do the opposite. You can have your text, encode it, get your representation, and then just decode the video sequence. And again, that's the basic approach nowadays for the state of the art. There is the broad picture. Now I'll explain what we have been doing together with Amanda and Laia. So the first main contribution was the how-to sign data set. So this data set was collected at CMU by Amanda Duarte, that's this lady over here. She could not be here today with us. But basically, we took advantage of the unique installations, the studio they have there. This is the Panoptic Studio they used to have at CMU that has multiple cameras and that facilitates predicting the 3D poses. So our data set has 3D poses, which is somehow unique for this field. We also, later I will develop on that. Also, instead of saying, okay, let's start from scratch, something that we did is instead of trying to figure out which are the sequences, the utterances that we want to translate, what we did is we took an existing data set, the how-to data set that already existed, that went from speech to language, and many other things by Ramon Sanabria, who is speaking later this afternoon. I think he's somewhere in the auditorium. What we did is we recorded on top of that, right? So we hired interpreters, and we gave them this transcription in text, and they were signing all these utterances. That's basically the contents of our data set. So we had these recordings on Green's studio. These are what you can see here from a frontal camera and from a side camera, also with depth, and that's most of the data set is like that. And then for one portion, we also have these multi-view recordings that were recorded in the Panoptic Studio, right? So that was much more complicated to record, so we could all record it for a subset. In addition to the recordings, we also extracted the poses with state-of-the-art tools like OpenPose. I think now we also have them with MediaPipe, and also by the tools that in the same Panoptic Studio they have to extract the 3D poses. So we have 2D poses and 3D poses. Overall, how to sign this data set that you have here. So there have been different data sets on continuous sign language in the state-of-the-art. So we work on American Sign Language. That's the amount of vocabulary, the amount of different words that we have, the number of hours that we have, different signers, and our setup is in a lab, right? So everything is very controlled setup. And basically, as in the how-to original data set, they were tutorials from YouTube. That's the type of videos that we have as well. Recently, there was another data set on American Sign Language that it's much more open from the web, and also this one from British Sign Language, which is from Broadcast TV, that came after hours, which are large, but not in such a controlled setup. So what have we done with this data set? So the first step we took was in testing human motion transfer. So basically what we did at that time is we took a model called Everybody Dance Now. Maybe you have seen that, and we just trained it with our model. So what we are doing here is transferring the motion from the lady on the left to the lady on the right, conditioning, so extracting the poses, and then condition the model with these poses. So what you see on the right is the synthesized video. Later, and that's a CVPR from this year, we address a more practical problem, which is sign language video retrieval. So here, what basic idea is to learn some joint representation, so train neural networks that will map into the same representation the utterances, the parallel utterances that come from the video or from the text. If we can do that, if we can train these encoders, later, if we make a query, a textual query, we can extract the representation and look in this embedding space whether if our query is textual or if it's video, but let's say it's textual, we can find the videos in our data set that are nearby in this embedding space and solve the nearest neighbors problem, for example, right? Notice that that's quite important because nowadays if you upload a video, let's say on YouTube or whatever platform, that video is not indexed. You cannot search for it with text, right? Because there are just signs. And that's what we are trying to solve here, because now with this technique, you could upload a sign language video, and you could query that sign language video with text. There's a big challenge for us to train with these encoders, which is basically that how to train especially this part, the sign language video embedding, because what we needed to train this video embedding would be some type of alignment between the videos that we have and the, let's say, words or tokens that we get from the language, which they are not aligned. So the video that we record, we have the transcription, we have the video, but they are not temporally aligned. And we would need to align them to record it, to train, to be able to train the encoder. So that's the main challenge and the main contribution of the paper. So how to train this video encoder without an annotated data set at the time level. So this temporal alignment, that's what we are missing. So what we did is we exploit the text transcription that we got from how-to, and we use some other techniques called sign spotting that now I will describe. But basically, we have some type of weak alignment, weak temporal alignment that allow us to train our video encoder. We exploit two techniques that were already in the state of the art. The first one is called mouthing, and I'll use it with an M. And it exploits the fact that many interpreters, when they are signing, so they are going from some spoken language and they are interpreting in signs, they are also mouthing, so they are also kind of pronouncing what they are translating. Even that's not necessary at all, right? But they do that. But then with some sort of, let's say, lip reading, if we know what they are transcribing, we can really find which portion of time maps each word, let's say. So this word, I think was apple, no, happy. We can find in which part of the video the word happy will appear, because the person will be mouthing happy, and we know we are looking for happy. With this way, we can extract some weak annotations. So that's technique number one. And the second technique, also from another work, it's if we have a visual dictionary, and this is really a lookup table, and that they exist. There are visual dictionaries that give you this spoken word goes to this small video snippet, right? We can, and again, we know more or less where that word should be because we know it from the how to sign data set, and we also found the mouthing. We can identify which part of the video maps with the word that we are trying to find. And again, we obtain a lot of weak annotations, and we can fine-tune and train our video encoder. After that, we can run our queries based on video or on text, and we obtain the videos that we retrieve. In terms of results, what you can see here on the first two rows is what happens, especially the first one would be kinetics is a general purpose video dataset, very popular in the computer vision community. So if you train your neural network, your video encoder with kinetics, and then you try to look to solve all the retrieval problem, to learn features, it doesn't work. I mean, this performance, it's really bad because these are recalls, and the higher the better. So it's necessary to fine-tune the video encoder with sign language video. If use this Bob SL, which is a sign language, British sign language, to fine-tune it, things improve a lot, but that was using some other annotations. And with our technique, by adding the mouthing and then spotting dictionaries, and here D1, D2, D3 means different iterations, so we run it more than once. So we first find some words, and because we find some words, these are anchors for other words, and then we improve. We kind of improve the quality of the video encoder, which in the end improves the quality of the retrieval results. That's the basic idea. Other application we have explored, this task of topic detection, which means given a video, let me know what's the topic about. So that's easier than translation, but still it's an old task that we explored. And if you're interested in that, you can go now to the poster session, look for Alvaro, and he will tell you about it. We have the main task of sign language translation that I was mentioning. We had a student who ran it on a very popular data set called Phoenix. That's kind of what everybody's using for translation, and we obtained some scores. And we also ran it on how to sign. You can see scores are worse than with Phoenix, which means that how to sign is harder than Phoenix. Actually, Phoenix is the data set that's only about weather broadcast on broadcast TV. So, sorry, weather forecast on broadcast TV in German. So, but still it's not random, so we are doing something. And what it's also, that's something that if you're in the field, you will appreciate. is that we have already released an open source implementation of this model. So there's a lot of engineering work behind here adapting FairSec that is very popular in the NLP community. So we adapt it so you can encode your video features and use it with FairSec to try to address this translation task. If you want to know more, later you can go to the poster session with Laia, and she will tell you how was our participation in a recent workshop on EMNLP. And just to come as a conclusion, I would say that sign language video understanding is a very nice and exciting research venue because it combines kind of a little bit of everything. You need vision. I think in order to solve that, we will need 3D because I think it's very, very difficult to just try to interpret video with 2D. You need language, and if you really want to do it end-to-end and from speech to sign language, then you also can think about speech. So as many of you are in one of these fields, maybe you want to look at that. That's a real exciting multimodal problem. And also, if you happen to visit Madrid in the next days, I invite you to go to this exhibition called Código y Algoritmos in the Espacio Telefónica, somewhere there, up to the 16th of April, where there's a space where we show in some part this experiment. And that's it. So thanks a lot for your attention. And if you have any questions.
Thank you. Questions? Yeah, there, at least.
My apologies if you answered this in the talk, but do you do translation from one sign language to another sign language?
No.
What? Okay.
From sign language to a spoken language. No, we didn't try. I guess it's a new venue. I don't know if somebody has tried, but.
Yeah. My question goes in the same direction. So if you want to do that, it's better to go through text, or would you go from directly video to video?
Yeah. I think that nowadays, probably you will, if you try to do this, you will have a problem with that you don't have enough data. That's my expectation that you'll get, and with sign language video. So there's so scarce sign language video data and even less annotated. But there's so much, all these textual large language models that I think they can help a lot. I think there's a lot of potential there to see how to export these large language models to be combined with these visual language models. So my advice is this, yes, that you try it, at least by now, and maybe someday if we have huge amount of sign language video understanding, it would be interesting, it would be possible to go from one to other, but nowadays it's really hard to get the videos, and if you want them annotated, I think that doesn't even exist, right? So probably I would suggest to take some intermediate steps. So that's why there's all these long arrow with some intermediate steps, because that's what people have been looking at.
Thank you.
More questions? I do have a question.
You have a question? Okay.
Yeah, but I think I will ask you at the lunchtime.
Yeah, okay.
And let's thank the speaker again.
Yep.
Now.
Okay, if you allow me, yeah. Okay, now I'm done as a speaker, okay, but in previous years I was organizing this event, but now Laia is organizing that over there, so maybe I suggest first that we give a big round of applause for the great work. And she will tell you, just come here, just come here, please, okay?
Okay.
She will tell you now how does lunch and afternoon sessions work, okay? Thanks.
Yeah, thank you. Okay, so we are going to have lunch at Sala Agora, which is not in the Vertex building. So we'll have 2 volunteers guiding you on how to get there. But if not, you can just search for Sala Agora in Google Maps. So this will be until 3:30, and then we will have here, you can find them. Yeah, so we have 2 more sessions in the afternoon, which for them we'll have to come back here. And then we will do our Turrons and Cava finishing event again at Sala Agora. Yeah, so next place is Sala Agora, then we'll have to come back here, but it's not in this building, it's a classroom that is in Vertex building. You can also find it in Google Maps. And then finally we'll go to Sala Agora. So now please follow the volunteers. They have these yellow badges, and they will be able to guide you there. Thank you. Vale. Sí. Merci.